Welcome to CS2 219 online, not 202, even though we're doing it on Twitch where we normally do the 202 lectures. So yes, welcome. For those of you that are watching live, welcome. And for those of you watching on YouTube later on, then we had it live on Twitch, so that's why I mentioned Twitch. So today we are going to be covering a couple of interesting algorithms. Well, one algorithm really, and then the rest of the stuff is going to be basically a bunch of computer arithmetic or binary arithmetic in a way, since that's what computers are using. And this is chapter 11, but also at the end I want to briefly cover chapter 12, which I'm just going to point out what's in it because I think you should all know that. I mean, it's like the truth table for the and or, which I think we all know at this point from CP 100. So in fact, a lot of the stuff that I'm going to talk about today you might have covered in CP 100 possibly, such as maybe you covered Booth's algorithm, and if not, you at least cover addition and subtraction in binary. So this is a reminder that tomorrow or Friday you do have your live discussion session with the TA on WebEx. So don't get confused on that. So it says we have 7 viewers. I don't know how much because that's always not exactly accurate. It's like delayed, so you could have a different amount, more or less. But it doesn't matter because either way I was going to record this without an audience. So the good thing is now you guys can ask questions. And I think this is one of those algorithms that I find people have a hard time with, at least the Booth algorithm. And I will try to demystify that. But before we get to that, let's kind of just jump into the beginning of the chapter, which is actually talking about the CPU. So now we've talked about memory. We talked about I/O. We talked about external storage, such as a hard drive. And we've talked about cache as well. And we mentioned, though, didn't really go into detail into the system bus, right? And so that only leaves us with one big major component that we haven't talked about yet in the class. And that's the CPU. And it's the most important, per se. Frankly, everything around it that we talked about supports the CPU. And so that's what we're going to be talking about next week, the CPU in detail and those kind of things. But before that, we kind of have to understand the language that the CPU uses. And it doesn't use English. It doesn't use decimal. It uses binary. And because it uses binary, it's good to understand a little bit about how that binary can be translated into other things. So I think at the end of last lecture, when I was going over chapter 10, which is a very, very short chapter, I showed you basically, if you didn't remember what binary is, we talked about binary, and we did a very basic way of converting from decimal to binary and from binary to decimal, which was just taking the location of the digit and multiplying it by a power of 2. Okay? And so that is kind of the starting point for today. But before we jump into that computer arithmetic, they do have in the chapter in section 11.1, which is introducing the ALU, which we have talked about before. What is the ALU? That is the Arithmetic and Logic Unit. So that is going to be the part of the computer that actually does the math, and the math being the arithmetic. It's not complicated math because at the end of the day, it's all logic gates. It's all and, or, and not gates or other variations that are derived from those 3 gates. And so there is a way, and I think that's basically what chapter 12 is how to create a calculator using logic gates, which if you took CP 100 lab, you probably did using a breadboard. And so they say and they claim that actually the most complicated part of the CPU is indeed this ALU because it's doing all the math and logical operations on the data. So as I was saying earlier, all the stuff that we have talked about is basically to support this ALU, memory and external storage, I/O, all these things are done so that we can actually bring the data to the CPU, and by that I'm saying bring it to the actual ALU so that it can actually do the computations it needs and then send them back out, okay? And so the way that the ALU is actually processes data is just binary. It's just Boolean logic, basic Boolean logic, which is what it says here, which is those truth tables. And so to be able to talk that language, that's what we're going to be focusing today, is talking about how these arithmetic operations are performed. And so first of all, we have what we kind of mentioned yesterday, which is the speaks in binary, and then in binary there's zeros and ones. And we talked about a way of representing, I think we might have talked about a way of representing positive and negative numbers in binary, but if not, let's go ahead and talk about that now. So what I want to talk about is 1's complement and 2's complement. So, but before that, let me introduce you to the idea of keeping a range of numbers in binary. Okay, so you know what I showed, I think what I showed last time was just regular binary. So if we have something like this, you know, if we're trying to convert this into decimal, we take basically the position of the digits and use that as the exponent to our additions here. And so, for example, this means that 2 to the 0, well, this is what these are. 2 to the 0 is just 1. 2 to the 1 is 2. 2 to the second is 4. And 2 to the third is 8. And so we take the positions of this that are 1 and add those digits together. So we're going to add 8 plus 2. So the equivalent of 1 0 1 0 in binary is going to be 10. Okay. And if we wanted to go the other way around, so let's say we want to convert 20 into binary, we we take the biggest power of 2 that can go in here. So that's 16, which is 2 to the 4. And then we subtract that from our number and we get a 4. And then we take the biggest power of 2 that fits in that, which that's actually nice because it's exactly 2 to the second. And so that basically means that we need to have a 2 to the 4 and 2 to the 3 that are 1. Oh, sorry, 2 to the second that are 1. And then the other digits, which would be 2 to the third, 2 to the first, and 2 to the 0 to be 0. So that means that the binary equivalent of 20 is that. And that's what we said yesterday, and hopefully you've seen that video. And if you haven't, then this is part of what I'm talking about there. Okay? And so, you know, this works great for positive numbers, but you know, if you're keeping your numbers in some sort of range, so for example, you know, when we talk about addresses like 16-bit or 32 bits and so on, you know, you can just add leading zeros at the end of here so that you can make it that big, right? So if you wanna always have something that is 8 digits long, and this 20 is 5 digits long, then you can just put 3 zeros here. It's kind of like saying if I was using decimal system and I wanted to store the number 45, but I always wanted all my numbers to have 5 digits in length, then I could just put some leading zeros which don't change the number, right? We don't want to put trailing zeros like this because that changes the actual number. Now this is 450,000, right? Whereas this is still 45 because these are insignificant. So, you know, you can apply the same concept to binary by just putting leading zeros like that, okay? And this is great and works amazing for positive numbers. But the question is, how do we represent negative numbers in binary? And so the most simple version of that is, okay, why don't we just keep the numbers as they are, positive, but then if we want to like know that a number is negative, then let's just keep track about that somewhere else with a single bit. So we could call that some sort of sign bit. And if it's 0, we'll say it's positive, and if it's 1, we'll say that it's negative, okay? And so that works cool. And then if you want to associate that with the same number here, you know, then we can just use the last digit here and just append that as to be the sign bit. And so all of a sudden now we can go ahead and make this be a 0 for a positive 20 or 1 for a negative 20. Okay? So that could be negative 20 and this could be positive 20. Now, what are the side effects of doing this approach? The side effects of doing this is that you are sacrificing 1 bit for keeping track of whether a number is positive or negative. And there are additional side effects about that. If your number gets big enough, so suppose that, let's say we were keeping the number 15, the number 15 in binary, okay? So the number 15 in binary would be, I'm presuming to be, if I got the math right, it's going to be this. Because if this is 20, then that means that that's 14, or sorry, 19 would be 0, 0, 0, 1, 1. And then 18 would be this. And then 17 this. So, okay, 16 would be this, okay? So let's say that would be 16 here. And then 15 would be 0, 1, 1, 1, 1. Okay, so let's say that we were keeping positive 15 and negative 15. Okay, in using the system that I'm talking about here. Okay, using that system, you know, I know that this is actually 15 in binary, and so if I want to use this last bit as a number for positive or negative, then I can just change all these to ones to represent negative 15. Okay, this is cool, but the problem is this: what if I add 1 to this number here? If I add 1 to this number here, 16 is represented like this. However, by doing this, I run into a problem, because if I'm using my system where that last bit is actually the representation of whether something is positive or negative, all of a sudden now, using this rule set, that should be some sort of negative 0, okay? And so the limitations of using that last bit as your sign bit basically makes you lose a range of numbers, because now if your range is up to only 4 digits, then you can only keep there anywhere from 0 to 15, positive or negative. If you go bigger than that, so you go to 16, or you go smaller than negative 15, then you basically, in the case of negative 15, if you can't increase it anymore, because you will need to have an extra bit here. And so that's the only issue with doing a sign bit, is that you lose range of digits. Okay, so this system is cool, of being able to just have, you know, keep things just the same way that you're using them, but simply make this last bit to be a 1 or a 0, positive or negative. But it has some side effects when you're trying to do addition and subtraction in binary. Okay, so how do you do addition and subtraction in binary? It turns out that addition is relatively simple, and it's actually done the same way that you would do it in regular like math, in decimal. So if you want to add two numbers in binary, all you gotta do is just imagine that they're in decimal and add them together. So, like, for example, let's say that we're adding what's this in binary? So this is 2 to the 0, 2 to the first, 2 to the second. So that's 4 in binary. Okay. So because because this is 0, 0, 0, 1, 1, 0, 1, 1. So okay. Yeah. So let's say that we're adding 4 plus 3. Okay. So 3 in binary would be this 1, 1 here. Okay. So we would basically just put in 1, 1 here. You can fill the leading digits with 0, and then just imagine that it's regular math. This becomes a 1 here, 1, 1, and 0. So this would be the answer of basically 4 plus 3 in binary, which is 7. Is that correct? If you don't believe me on that, we can do that here. That's a 4, then that's a 5, that's a 6, and that's a 7. So it works fine. However, let me put one that might be kind of tricky here. Let's say that we're adding 3 plus 3, okay? Which we know is supposed to be 6, right? But you might naively be like, oh, well, this must be 2, 2, 0. But no, because this is binary, so there is no such thing as a 2, okay? So when you have a situation where you're adding 1 and 1, what is 1 and 1 in binary added? Well, 1 and 1 in binary is actually going to be 1, 0, because you go from 0, 0 to 0, 1, and then the next digit is 1, 0. So it's kind of like your 10 in decimal, in the fact that when you run out of symbols, you carry. So like when you're doing something like 6 plus 6, what you do is you figure this is 12, so you put 2 here, and then you carry the 1 over, right? So if this was the addition of like maybe 16 plus 16, what you do is you carry that 1, and now you do 1 plus 1 plus 1, which is 3, right? And so this is how you do your math in like elementary school. So over here, this 1 and 1 is not going to be 2. It's actually going to be 0 with a carry of 1. And so the same thing's going to happen here, except here it's not 3. Here it would be 1, 0 plus 1, which would be 1, 1. So here you put a 1 and you carry a 1. And then you do 0, 0, 1, which just brings you a 1 down. And so the answer is actually this, which we can see here was indeed 6. Okay? So that's the only sort of different or / weird thing when you're doing math in binary, that you have to kind of remember that when you go over, when you have two ones that are being added together, what you do is it basically equals 0 with a carry. Okay, so this plus this in binary is always going to be that, which If you were doing it this way, it's like you put a 0, then you put a little carry here, which you bring down. Okay, so for those of you that are watching live, you good on that, or are there any questions? I'll take that as a no. So this works fine, but it breaks with negative numbers with the system that we've implemented so far. Because here's the thing, in regular math, if we have something like 2 and then we do -3, you know, plus -3, then this should give you -1, right? Because 2 plus -3 is the same thing as 2 minus 3, which is equal to -1. Yeah, this should definitely give you flashbacks of CPU 100. That's a good thing. So enjoy that PTSD. Okay, so yeah, so this should give you a -1, right? But here's the thing. If we use our system that we set up, which is basically making the last bit to be a sine bit, this whole thing breaks down if you just want to do the math like this. So like if we're trying to do something as basic as, you know, let's say that we have 4 valid digits and then we have the sine bit. So let's just say that we're going to add 1 and then add that plus 1, okay? So -1 plus 1, okay? Or, you know, yeah. Don't even think about subtraction. Just think about that addition, okay? So -1 plus 1 we know should be equal to 0, right? Because that's the same thing as saying 1 minus 1. And so because we're using the sine bit as as just the last digit there, you know, if we just try to do the addition sort of how I showed you, then this becomes a 0, this carries a 1 there, and then that becomes a 1, and then 0, 0, and then 1. And this is actually the equivalent of -2. But that's not what we wanted. We were doing -1 plus 1, which should have given us 0, but it gave us -2. Therefore, this fails, right? We got to have some complicated logic to be able to figure this out. What could we do in that case? Well, you know, we have to realize that one is positive and one is negative, so maybe we need to like sort of subtract things together, but that it just makes your life hard. And so this doesn't really work out well. And so the proposed alternative to keeping track of positive and negative digits is going to be 1 and 2's complement. So what is 1 and 2's complement? 1 and 2's complement, let's do 1's complement first. 1's complement is going to be the version of keeping a signed bit, or the idea of keeping, the idea of keeping a signed bit, but to represent a number, you're actually going to use a different range. You're going to start out with 0. Let's say we have 4 digits. So you start out with 0 here, and then you get 0, 0, 1, which becomes a 1. Eventually, though, once you get to 1, 0, 0, and then eventually 1, 1, 1, what this is going to be is this is going to be the biggest negative, or I guess the smallest negative number you can have. You know, I was thinking biggest because it's the biggest number, but it's a negative, so it becomes smallest, I guess. So, for example, here, you know, let's, again, we're using that last digit to keep track of that. So let's just say we get something like 0, 1, 1. That is going to be, what we said is 7. It should be 7, right? Let's see, 1, 0 will be 2, 3, 4, 5, 6, 7. Yeah, 7. Okay. And so that will be 7. And then from there, because we're going to use this last digit to keep track of the sign, when we get to 1, 0, 0, 0, that is actually going to be a negative number now. But it's not going to be -0. It's actually going to be the biggest negative number that we can have, which would be -8 or -7. Negative 7, I think. Yeah, I think -7. Okay, because then 1, 0, 0, 1 would be -6. 1, 0, 1, 0 would be -5. 1, 0, 1, 1 would be -4. 1, 1, 0, 0 would be -3. 1, 1, 0, 1 would be -2. 1, 1, 0. Oh, I might have actually been off by 1 here. -1. Yeah, okay, so never mind. My bad. That actually no, this is okay because this is 1's complement. So yes, this is actually right. Yes, okay. I was getting freaked out because 2's complement. Okay, so yeah, this would be the equivalent of how to keep track of this with 1's complement. Okay, which as you can see is weird because there's 2 zeros. There's a +0 and there's a -0, which just like blows your mind. Like, how can there be 2 zeros if there's 0, right? And this is cool. This is an alternative, and this actually makes the math easier, but it still doesn't solve the problem that we have. To solve the problem that we have, we're gonna use 2's complement. 2's complement is 1's complement plus 1. Okay, and so, but I guess actually, yeah, okay. I'll tell you 2's complement because really 1's complement is just kind of like FYI kind of thing, but 2's is one that we want. So 1's complement is basically you flip the digits to know what you have. Yeah. Okay, so the algorithm to convert from a regular digit to a negative number is you're gonna flip all the digits to their opposite sign. Okay, so if you want to convert, for example, 1 into -1, you convert all the zeros. So you take the 1's complement, you convert all the zeros into 1's, and you convert the 1's into 0. So that becomes the 1's complement for -1, which does match what we have here. Yes, okay. Oof. It came back to me as I was saying that. Okay, so great. Similarly, if you want to convert 7 into -7, notice that you're just flipping the bit. So you're flipping the 0 to 1's and the 1's to 0. Okay, so yes, I think you got to do this as a program in 218. But yeah, that's the only trick to this. So for example, 3. How would you do 3 in 1's complement? So you know, let's say that we have a lot of extra digits for some reason, and then we have that, okay? Because we know 0, 0, 0, then 1, then 2, and then 3, okay? So the 1's complement of this would be to just basically flip these all to 1's and then flip these all to 0. And that would be the equivalent of -3 versus 3, okay? So it's a nice little quick convenient way of keeping track of things. However, it's not enough because if we want the algorithm that I'm going to show you next to work out, then you're going to need 2's complement. In fact, I think there's a better reason as to the why 1's complement is not great. In fact, I don't even think the book mentions 1's complement. It just kind of goes directly to 2's complement. Oh, no, here we go. There are several drawbacks. It is inconvenient to test for 0, and so on. So it's just inconvenient. I mean, I think the biggest drawback is that we have 2 zeros. We have 0, 0, 0, and 1, 1, 1, both representing 0. And I guess from a standpoint of view of you trying to be like super efficient with your bits, you know, because you want to keep the biggest range possible, it's pointless to have 2 things that actually represent 0, because, you know, suppose that you have a range of 254, or sorry, from 0 to actually 254 bits, okay, or sorry, numbers with this number of bits, because you have 2 zeros, versus 255 if you only had 1 0. So because you're that cheap per se and you really want to get the most out of your computer, then we want to only have 1 0 representation. And so the solution to that is 2's complement, which is doing 1's complement and then adding 1 to the result. Okay, so that's the important one. That's the one that you should really know, because that's what's actually implemented in computers. So 2's complement is going to be to take, so if we have something in a positive value, so let's say that we have, like, I don't even know what this would be in decimal. Here we should have a binary to decimal calculator ready to go. Where's my mouse? Here we go. That might come in useful throughout the lecture. I did actually write some C++ code to convert stuff, but I don't want to pull that up yet. Binary to decimal. Rapidtables.com is the one that I was using also in 202. So this will be 0, 1, 1, 1, 0, 1, 1. So that's actually 59 in decimal, okay? So what we want to represent is negative 59 in 2's complement. What we're going to do is we're going to take the 1's complement first, which is just flip the digits around. So make this a 1, 0, 0, 0, 1, 0, 0. So basically we flipped all the bits like that. And then just add 1 to that value. Okay? So it then becomes 1, 0, 0, 1, 0, 1. For the addition, refer to what I just said about pointer arithmetic, which basically tells you that, I mean, the only 2 cases you might have are that the last digit is a 0. If it is, then just make it into a 1. If it's already a 1, then make it into a 0, but make the second digit flip that. And if that's already, flip that if it's a 0 to a 1, and if it's a 1 to a 0, but then you got to flip the third bit, and it's a chain, I guess the worst case scenario is if after you take the, let's say you take the 2's complement of 0. Yeah, actually. If we take the 2's complement of 0, it means take the 1's complement plus 1. So that would make it all 1s. But then when you add a 1 to it, this becomes a 0. This becomes a 0. This becomes back a 0, 0, 0, 0, 0. And then you get a 1 after that. However, because this is the amount of data that you're keeping, because that's the size of your registers or whatever, this sort of falls out and disappears into the twilight zone of computers. And so that's okay, because that's good for us, because we've sort of solved the problem by adding 1 of having two zeros, a positive and a negative 0. And there you go. That is 2's complement. So just flip the bits and then add 1 to it. And it's a very nice and clean way of keeping both positive numbers and negative numbers. And that's actually how computers are kept. So I think this is the time that I wanted to show my ID1 code. Yeah, okay. So now I'm gonna switch over to this. And so here's some code. And if you want to run it yourself, you can copy that URL. And so, in fact, I can type it out. Ignore the random add. And let's go ahead and run this. Or, I mean, I actually already ran it. What you see there is the output. But essentially, to prove to you that this is how it's actually keeping the data, you can use the bitset library to help you in converting binary to decimal. Or, sorry, decimal to binary. And so I went ahead and created a couple of variables. One with 0, one with 1, one with 5, and then a couple of negative values, negative 1, negative 2, and negative 5. And so here we can see that 0 is indeed a bunch of zeros. 1 is just a bunch of zeros with a 1 at the end. And then 5 is 101 at the end, which we saw that's actually the correct thing. And then notice that negative 1 is actually a bunch of 1s. So how was that handled? Well, they took the 2's complement of this, which would have made everything 1, 1, 1, 1, and then this is 0. But then when you add that plus 1, it became a 1. So now that is going to be our negative 1. And notice that one for negative 2, all that happens is it starts sort of counting down. It's sort of a natural thing that would happen, because 2 in the positive would make this a 1 and this a 0, which would make everything else 1s, and then here would be 0 and then 1, but then this would become a 0 when you do the addition. Here, I might have said that wrong. Let me just draw you what I mean by that. So, that means that if we have a 2 like this, when you take the 1's complement first, this becomes that, but then when you add the plus 1, then this becomes a 1 and this becomes a 0. Okay, which is exactly how they got that. Finally, negative 5, it's basically taking this 2's complement. So basically all those become 1s. This becomes a 0. This becomes a 1. And this becomes a 0. Let's do that one. That does not feel right, but let's do it. So let's see. We got 0, 0, 0. But, well, the leading zeros don't matter. But, just put a couple of them. And so if we take the 1's complement, it's going to be 1, 1, 1, 0, 1, 0. like such. And then we add 1 to that, which would be 1, 1, 1, 0, 1, 1. But there, it looks different. Oh, I have a bug in my code. That's why. I have a bug. I was copying and pasting, and I forgot to change this to be an F. So that's actually not the answer. So, yes. Error. I probably have. It's because I ran this a long time ago. So I need to like refresh this and make a new one. Yeah, I was like, that doesn't look right. Okay, so there we go. That's the actual answer that we got. So that was indeed what we got. So yeah, but see, hey, we can now debug binary because we know that that is what the answer should be, right? This here, 3 1s, a 0, and 2 1s, and here you can see 3 1s, a 0, and 2 1s, and then of course the leading ones as well. But yeah, so great. So now there's a new link. This one does not have a bug in it with the F in there. So indeed F in the chat. So here you go. Okay, so what's the other thing I have here? Ah, that's for when I get to floating points. So that's going to be your 2's complement. Okay, so now that we did that, we can actually perform our mathematical operations and they will work just fine. So if we have, let's just use the ones that we were having right here. So let's say we're doing -5, which is going to be this thing that we have here. And then we are also, let's go ahead and add 5 to that. Yeah. So they should cancel each other out, right? So, 0, 0, 0, and then 1, 0, 1. Okay. So that, let's add those together. And again, this should be -5 and this should be 5. So this should give us a 0, right? And so, to perform this highly complicated mathematical operation, we are just going to do what I showed you before, which 1 and 1 will give you 0 with a carry of 1. Then 1 and 1 will give you another 0 with another carry. And then that's going to give you 0 with another carry. Oh, wait. Yeah, we're good so far. And then that's also going to give you a 0 with a carry. Lots of carrying around, Eventually, they get to 1 there. However, that 1 is outside of the block of text here, so again, it gets just thrown away. So the answer is indeed a bunch of zeros, which is correct. So by using 2's complement, we simplify the way that the ALU can do just arithmetic in general. And by the way, suppose that you wanted to do something like 8 minus 3. How would you do this in the ALU? Well, you would actually just do 8 plus -3. And how do you convert 3 to -3? Just take the 2's complement of that. So, and of course, this all depends on the number of bits. So let's say we're dealing with something that is an 8-bit system. So what is 8 in binary? I think that's going to be 1 with 3 zeros ahead of it, because we said that 1, 1, 1 was 7 before, right? Yeah. So basically, that's 8 in binary, and then we know that 3 in binary is that. And so if we're dealing with a system that is 8 bits long, let's just go ahead and throw in the leading zeros there. So 1, 2, 3, 4, 5, 6, 7. So wait, 2, 6. So one more, 8. And then for this one, we're going to add 6. So 2, 4, 6. Okay. So what we're going to do is we want to do 8 minus 3. So we're going to take the 2's complement of 3 to make it into a -3. So just 1, 1, 1, 1, 1, 1, 0, 0, plus 1, which would give us 1, 1, 1, 1, 1, 1, 0, 1. Okay, now that we have taken the complement, it's just as simple as doing the addition of 8 plus -3. So just doesn't matter which one you put on top or bottom. So I'm just going to put this one on bottom or top because it just looks prettier that way with the zeros. Let me make sure I get that 1 in the right spot. So that goes here and then here, here, here. But again, it doesn't matter who goes on top or bottom. Just like in regular math, it doesn't matter. Whatever that property is, it's like A plus B is the same thing as B plus A. I don't know. Commutative, transitive, one of those names. Math person knows. Math person, please tell us. So yeah. Okay. So just add them together. So just make sure the only thing you can really mess up here is like if you don't keep your lines straight, like I'm not doing. So like where like things can get crooked and you might add the wrong columns. So 0 plus 1 is just a 1. Then this is a 0. Then this is a 1 here. And this becomes a 0 plus a 1. Then this becomes a 0 plus a 1. This becomes a 0 plus a 1, 0 plus a 1, 0 plus a 1, which is just 1 here. Gets thrown away. So the answer to this is 0, 0, 0, 0, 0, 1, 0, 1. I think if I didn't mess with my zeros, then that's good. And is that the answer? Is 8 minus 3, 5? Yeah, I think so. So, yep. We succeeded in doing math. 101 is 5, yeah. So, hey, it's like we're back in kindergarten, but for computer. Well, not elementary school, for computers. So, as you can see, this makes life 10 times easier for doing arithmetic if you're using 2's complement, okay? So, that is going to be sort of the first part of the chapter. So, we can... They do give some cool formulas that, you know, if you want to consider, like, you know, how much does an 8-bit will represent? Well, it represents 2 to 255, right? And if you want a mathematical formula to figure out the sequence of bits, then you can do A is equal to the sum from I is equal to 0 to n minus 1. So you can think of this like a for loop. And then 2 to the I, which is kind of what we were doing basically earlier. That's for the regular one. For sine magnitude, the first method that I showed you, where you just, you know, you still keep them as positive numbers, but you put a 1 at the end if it's a negative number. That one is basically this. In fact, here, let me just copy and paste this. That's just basically this with a slight modification, which is I is equal to 0 n minus 2, not minus 1, but minus 2, because we lose 1 bit. And then 2i ai if an minus 1 is equal to 0, if an minus 1 is equal to 1, and then just put a negative in front of that one. Okay, so that would be for sine magnitude. And then finally, for 2's complement, it would be a is equal to negative 2 n minus 1, a n minus 1 plus the sum. I can't do that symbol. It's tricky. There we go. The sum of I is equal to 0 to n minus 2. Again, minus 2 because you have one of those bits to be, it's kind of like your sign per se. So, yeah. Okay. So, there you go. That is going to be 2's complement. That's a big math formula if you wanted to code it out in a computer. Okay. So, okay, so you know how to do addition and subtraction essentially. Again, subtraction is just basically convert it into a negative number by taking 2's complement and then doing the addition, you know. So you don't have to learn a different algorithm to do subtraction. That's what the computer's going to do as well. So that pretty much takes us to multiplication, I think. Let me just double check my notes here to ensure that we have... Oh man, I'm super hot because my dog is behind me. Let's see if we got everything here. Yeah, you just make sure you ignore that carry as it falls out, you know, so that things don't get messed up. I guess let's give an example where something would overflow. Yes, Padme is just back there just generating heat. So, yes. Okay, here's an example that we generate an overflow, okay? Because overflows are important to talk about. We always talk about them, but I want to make sure you guys actually know what people say when they're saying, like, we just overflow, you know? When we say overflow, it means that, like, you know, let's say that we only have a system that can keep 3 bits like this, okay? If we have a system like that, then, what range of numbers can we keep in that? You know, forget about negative or positive numbers. Just talk about pure positive numbers. If that is the case, that we only have 3 bits, then we can basically keep from 0 to 7, okay? Which is a range of 8 numbers. Yes, because we count 0, okay? So, basically, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, then 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1, okay? So there you go, you have 8 digits in there. And so what happens when you go to 9? You know, because suppose that you're doing something like in binary, you're doing an addition. So you're doing 0, 1, 2, 3, 4 plus 4. Okay? Because the biggest number that you can keep is a 7, right? So if you're doing 4 plus 4, in the way that I just showed you, it's that. That's the answer, okay? That would be the answer of an 8, which is correct in binary. That would indeed be what an 8 is. But if your system can only keep 3 bits, you know, we throw this away, which is actually something useful, because when we're doing 2's complement, that's the reason that thing works, because we lose that extra bit if it's too big for the system. That's the good side of things. The bad side of things is something like this. When you're adding this in your computer, that 8 doesn't fit in the 3 bits, and therefore it actually, the answer that will tell you is a 0. That is the equivalent of what is known as an overflow, because basically you get the answer you get doesn't fit in your data type, and therefore it basically it breaks. Essentially, you get some bad number. You might get a negative number and so on. If you're here from 202 people, we had that happen with the car. That, you know, that was weird when we were adding basically A plus B, which in ASCII is like, I think 65 plus 66, which gives us something that is bigger than 127, which is the biggest number that we can keep in ASCII. And so, because it goes from 0 to 127. And so because of that, we got some negative number, or at least the computer interpreted as a negative number, which is just totally invalid in ASCII. So yeah. So that's an overflow, okay? So that's gonna be the sort of the only bad, scary thing that could happen here when you're doing this thing. An example of something, what I guess it would be called an underflow when it's negative number, would be something if we were taking like 1, 1, 0, 1, which would be, well, what is this? What does this represent? Well, let's take the 2's complement to find out. This would be 1, 1, 0 plus 1, which is 1, 1, 1. That's a 7. By the way, I guess I should say that 2's complement works both ways around. So if you want to, if you have a number that you want to make negative, you can just take the 2's complement to figure out what that is in negative. So like you can do, so you know, if you have 3 and you want to convert that into negative 3, you know, you take the 2's complement and it becomes 101, right? You can also, if you want to see what this is in positive, you can take the 2's complement again, and it'll bring you back to your original result. So like that, the 1's complement of that is 1, 0, 1, 0, 1, 0 plus 1 gets you the original thing of 0, 1, 1, which is 2's complement. Okay, so as you can see, it's circular. Okay, so take the 2's complement to see what it's a negative, take the 2's complement again to make it back to positive. Okay, so, you know, let's say that we want to take negative 7, which is 1, 0, 0, 1, and then we want to take the equivalent of negative 6, which would be 1, 0, 1, 0, right? Because it counts down, so that means it should be negative 6. And so, you know, if we're adding negative 7 plus negative 6, it's basically the answer that we should get, you know, or, you know, in math we should have gotten would have been negative 13. However, here, because we are only dealing with a 4-bit system, when we do this addition, we'll see that we get a 1, a 0, 0, 1. Okay? That, because we lose the 3, or sorry, because we lose the 1 there, it gives us as an answer that this is 3. But it's not 3, it's actually 13. It's actually, I think, a coincidence that this became a 3 and that. So, but yeah, we basically, we lose that. And so that is going to be another example of an overflow. Or again, I guess in this case, it will be an underflow per se. If this doesn't make sense so far, think about it in like decimal terms. You know, suppose that you have a credit card where you can only borrow up to $99.99. Okay, and then somehow you manage to borrow another $1 or another penny from this account. So right now, this is how much you owe. You owe 100. You basically owe $99. Okay, and that's the limit you're supposed to loan. But somehow you manage to loan one more penny out of this. So when you add that extra penny, so when you do minus another penny, then this becomes you owe basically $100. But because your machine can only keep 4 digits, Now all of a sudden it says that you don't owe any money. So hey, that's great. You basically just scammed them into not paying the money, right? So this will be the equivalent of an overflow in decimal, okay? So yes. Okay, so I think that covers that. So yeah, now we can move on to multiplication finally. So that's going to be Booth's algorithm, because if you try, so if you try to do multiplication like they sort of teach you in elementary school, it's not really going to work out in binary. Well, here, let's try with something basic. Let's do 2 plus 2, or 2 times 2, okay? So 2 times 2. But here it's positive numbers, okay? So if it's positive numbers and we treat it like we would treat something in decimal, we would find that, you know, it's pretty okay. So this would be 0 times 0 times 0, everything. And then this would be 0, 1, 0. And then this would be 0, 0, 0. And then we would add all these together. And so that would be 0, 0, 1, 0. And what is that in binary, guys? That would be a 4, okay? So you're like, oh, great, this works perfectly fine. And, well, here's the thing. Let's try to do it with a negative number, okay? So let's go ahead and do 2 times negative 2, okay? So let's take the 2's complement of this. So this will be 1, 0, 1, plus 1 becomes 1, 1, 0. So that's 2's complement of 2. So then we're going to basically do 0, 1, 0 times 1, 1, 0, okay? So this is basically 2 times negative 2. We expect to get negative 4 back, okay? And can this hold negative 4? Well, what is the 2's complement of 4? 4 would be this, and again, the 2's complement of that would be 0, 1, 1 plus 1, which would be 1, 0, 0. Oh, I see. Hold on, this is too small of a digit. Here, let's just add another digit to avoid that problem. By the way, if we add another digit here, that shouldn't cause any differences here. We just see a 0 everywhere else. You just get an extra 0 there. But yeah. Otherwise, we overflow here. So let's try that again here. So let's go ahead and take the 2's complement of what 4 should be. Okay. So 1, 0, 0. Just put a 0 there. The 2's complement of that is 1, 0, 1, 1 plus 1 would be 1, 1, 0, 0. Okay. So this is what we expect to get. This is what we're hoping to get when we do this multiplication. Okay. And again, because we have four digits now, if we take the 2's complement of this to figure out what negative 2 would be, it would be 1, 1, 0, 1 plus 1, which would be 1, 1, 1, 0. Okay, so this is okay. So we're going to do this multiplication with the hopes of getting that. Again, this works fine with positive digits, but as we will see, this is going to break down with multiplying negative digits. So first we do the first digit here, so 0 times 0, 0 times whatever is just 0. The next one is going to be just ones, so that would be 0, 1, 0, 0. And then essentially the same thing for the rest of them. 0, 1, 0, 0. I'm not doing anything different. Just imagine these were decimal digits right now. 0, 1, 0, 0. Okay. And now let's add them all together. 0, 0, 1, 1, 1, 0, 0. Okay. So expectation is to get this thing. And I guess actually this kind of sort of worked actually in this very special case, because technically if we drop the oh, dog wants to go, so go. Please, thank you. In this case actually it actually kind of worked out, because that is indeed a 4 in 2's complement. So would you look at that? Okay, that's probably a special case because we were doing 2 digits that are the same. But let's do it on something else that is not the same digits, okay? In fact, I have some examples somewhere here where bad things went down. Do I have some? No, I don't. Okay. But okay, this was just unfortunately a nice case where it actually worked out. But normally this should not work out. This should break down. So let's try to do 2 times negative 3, okay? That should be a little bit easier to break down. So again, we're going to do this as 2. and this would be 3, but we're going to convert it into 2's complement. So 2's complement of this would be 1, 1, 0, 1, right? Because it's 1, 1, 0, 0 plus 1, okay? So let's try that again with this, okay? So we're doing 2 times negative 3, okay? So again, I think the other one just happened to work out, which is misleading, because imagine I just told you that, hey, look, it works, and then you like just hard code that in your computer into your chip, and then you find out it doesn't really work, because it won't. It's supposed to break down. Otherwise, Booth's algorithm would not be part of what we're learning. So let's go ahead and try this again. So this first line is just going to be 0, 0, 1, 0. The second line is going to be a bunch of zeros. The third line is going to be 0, 0, 1, 0. And the fourth line is going to be 0, 0, 1, 0. Okay, basically, there's no science to this. Whenever there's a 0, I just put zeros in here, because anything times 0 is just 0. And whenever there's a 1, I just copy what's here. That's kind of like the nice thing about multiplying in binary, that there's no brain required to do it. Again, if it's positive. But again, this system won't work, right? So don't get too excited about that. But hey, at least the addition is easy in binary. So yeah, let's go ahead and add everything together here. So 0, 1, 0, 1, and then 1, 0, 0. Okay, so now this told us that because it's 4 digits, that this should be the answer, right? Is this the answer? Let's take 2's complement to find out what this is. 2's complement of this is 0, 1, 0, 1 plus 1. So 1, 1, 0. Oh God. That is actually 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. Okay, so that's 0, 1, 2, 3, 4, 5, 6. Jesus, we got 6 out of that. It worked again. Why did it work again? Is it maybe the problem when you multiply 2 negative things and it always works with 1 positive? Let me check. Now I'm questioning life here. Hold on a second. Why is this working? It's not supposed to work. Let's see. Multiplication. Now we can demonstrate that straightforward multiplication will not work if the multiplicand is negative. Oh, I see. Maybe if I flip them, it won't work. Let's try that. Or maybe Booth's algorithm just makes things faster. No. But I remember this not working. Let's try this again. But this time, let's actually flip the order of them. I don't think that should matter at all. But let's just try that. So this would give us a bunch of zeros here. 0, 0, 0, 0. And then the next one would give us 1, 1, 0, 1, and then a bunch of zeros. 0, 0, 0, 0, 0, 0, 0, 0. Okay? And then add everything together. Then we get a 0 here, get a 1, 0, 1, 1. And that's it, right? That's what we got before. So nope, that doesn't make a difference. So why, what is the case where this won't work? There is a scenario where this doesn't work. The problem is that each contribution of the negative multiplicand as a partial product must be negative on a 2n field. The sign bit of the particular products must line up. This is demonstrated in figure 1.1.1.1. However, if 101 is interpreted has a 2's complement value of -7, then each partial product must be a negative 2's complement number of 2 to the n bits as shown in that. Note that this is accomplished by padding out each additional bit. Is it because they're putting extra ones at the end of it? I think that might be why. Let's try that. Let's see. So they have an example there where they are doing 1, 0, 0, 1, and then they have 0, 0, 1, 1. Okay, and they're multiplying that together, but they are getting the right answer. But they're having to do padding to do it. Which is interesting. So let's see. Let's try to do that. So, well, here, let's just try to do it ourselves. So we should get 1, 0, 0, 1, and then we get 1, 0, 0, 1, and then just a bunch of zeros everywhere, which won't matter. So if we do this together and then we add it, we get 1, 1, 0, 1, 1, and then just a bunch of zeros. And if all we're keeping track of is 4 bits like that, then okay. Well, that would overflow in this example here, because the answer is -21. This is basically -7 times 3, but you can't keep that in there, so I would add an extra 1 here. And if I add an extra 1 in there so that I can keep up to 21, actually, can I even do that? I can keep up to 7 there, and then I can keep up to 15, and then I can keep up to 31. So yeah, I should be able to keep 31 if I do that. But that does make a 1 here, and that does make a 1 there, which does make this become 1, 1, 0, 1, and then this becomes a 0, and then this becomes a 0 again. Okay, I think this is good. Yeah, okay. I think it's gonna break when we do this. Okay, this might be good. Okay, so let me clean this up so we can see, because I think it'll break down with this case. Okay, so let's say we have the following scenario. Okay, so we have -7, which is being kept like this because we have 5 digits, or or you can even do 6 digits. Why not? And then we have the equivalent 3 in binary. Okay, so just to make sure that this is indeed -7, let's take the 2's complement to confirm that. So we get 0, 0, 0, 1, 1, 0 plus 1, which is going to be that. That is indeed 7 in binary. So good, that is good. Okay, and then the other one is good. Okay, so let's try to do the multiplication of this, because I think it's going to actually break in this case. Okay, we've just really gotten unlucky with the other ones, or lucky, I suppose, in a way. Okay, so let's try to do that. So the multiplication of the first one is going to just be the same number down here. So 1, 1, 1, 0, 0, 1. And then yet again the same thing for the next one. So 1, 1, 1, 0, 0, 1. And then there's going to be 4 lines of zeros, essentially, just all zeros. I'm going to, I guess I put them just to make sure that I don't make any typos or anything like that. So basically, there's 6 digits, so 6 zeros here, and then another line of these zeros, and 1 more line of zeros, like that. Okay, that's it. So actually, 1 more line of zeros, because yeah, 1 more line of zeros. So here, let me slightly move this a little bit here so that we can fit that last line of zeros in here. So 1, 2, 3, 4, 5, 6. Okay. Now let's add all of these together, go into arithmetic addition. So we get a 1 here, so that's a 1. We get a 1 there. We get a 0 there. We get a 1 here. This we get a 0, but we add 1 there. This 1 plus 1 plus 1 is 3, so that's 1 here and 1 there. And then this becomes a 0, and then this becomes a 1 carry, and then this becomes a 1. And then everything else is 0. Okay, so now we can only fit into this thing 6 digits, right? Because that's what we have up here. So the cutoff of this is basically 2, 4, 6. So right here, let me use a different color for that. Here. So this is the cutoff right here. Okay. the other digits are thrown away. Cool. I think we got it this time. All right. So the answer to this, negative 7 times 3, which we expect to get basically negative 21, right? 3 times 7, negative 21, is supposed to be 1, 0, 1, 0, 1, 1. Okay? Let's take the 2's complement to find out what this is in positive value. So that would be 0, 1, 0, 1, 0, 0, plus 1. Okay? Again, we just flipped all the bits like that. What is that? 0, 1, 0, 1, 0, 1. That's going to be, again, after we do add the plus 1 to it. What is this in decimal? Now I'm worried again. Okay. Where's my computer thingy? I think I'm starting to suspect as to the reason why why just yeah. Okay. So this is actually 21. Okay. So I think so. You know, this is unexpected per se. But I think we did get 21, which is what we expected, and so I guess that is a negative version of 21. So I think the problem with this comes in as follows. When we did the subtraction here, you know, we're only doing it on 6 digits. But if for some reason our answer wasn't cut off like we did here, then this 0 would cause issues. Like you can see that 0 could cause problems, right? So even though we're doing the subtraction there, we want to keep the result in 6 bits, then yes, the cutoff seems to be working fine. But I think the problem with this method, or the simple method, arises when we have the output being able to store more bits than the input, because then this 0 here would give us problems. But then again, my counter argument to that would be, well, whatever this digit is here, we can just extend it. If it's a 0, then fill the rest of the bits with 0. If it's a 1, then fill the rest of the bits with 1. So because of that, I guess this is okay. This is a valid way of multiplying, I guess, because I can't find out what's wrong with it. It's giving us the right answers. So that's surprising, because I seem to be under the impression that this was going to cause problems. I mean, I guess that is a problem. That is a tiny problem. What I'm telling you with the 0 being there. But there's also a tiny solution to that, which is if we're throwing away the digits, then it shouldn't be an issue. And if we're doing the multiplication, you know, if this thing kept 8 bits, then these 2 would be 1s as well, and these would be 0. And if that was the case, then there would be 2 1s here, and there will be 2 1s here, and then the thing would be okay, because that would actually be a 1 then. So yeah, so that's a little awkward, but hey, it works. But anyways, we're still going to talk about Booth's algorithm, because even though this is working fine, as long as you know that little extra fix, not even necessarily I would consider that a fix, it's just kind of something you would do anyways. Booth's algorithm, though, I do know that one of the reasons why it's used a lot in actual ALUs is because it is a lot more efficient than doing this, because this does require potentially a lot of additions. I know right now we don't have that many, but like if we're doing some serious math like this, and then the other one was like this, that all the ones that are 1s there will require us to do addition, right? So that actually would be a lot of computation. So Booth's algorithm is going to allow us to do the same multiplication in less steps, and apparently doesn't have any issues, which I still can't figure out the issue in the current version that we have. But yeah, okay. So yeah, interesting that this happened. This is awkward. Okay, so who's Booth? Booth is his name is Andrew Donald Booth, and he was born in 1918 and passed away in 2009, and he created Booth's algorithm in 1950. Okay, so I guess he was basically 32 years old about. So yeah, pretty cool. So or actually, did he do it in 50 or 51? I have two conflicting digits here, so either or, unsure. Okay, so Okay, never mind. I was just looking at something and I was like, okay. So let's talk about how Booth's algorithm works. And so it's tricky, okay? So let me put a couple of examples that I have here. So let's say that we are multiplying 0, 1, 1, 1, and then 0, 0, 1, 1, okay? So normally, if we're doing it the other way, which we, I guess, surprisingly found out that it's okay, this would require 2 additions, okay? Pretty much it would require, well, technically 4 additions, but 2 of those are just a bunch of zeros. But I suppose in theory, you do have to put them in because they're zeros, and there's no easy way of just skipping that. Like, we can skip it because it's obvious, like when we're doing this, like, yeah, there's a bunch of zeros and skip it. But when we're coding this, like, when we're not coding, but when we're actually implementing this at the hardware level, that's a hard thing to sort of skip. So Booth's algorithm is going to kind of help us with that. And so what you want to notice from this is, first of all, let's identify 2 terms. Those are the I think they're multiplicand and multiplicator or something. Hold on, let me see what they're called. Multiplicand and multiplier. Okay, so there's 2 terms. There's the multiplicand. Here, let me write them because that's hard to pronounce. We have multiplicand, and then we have multiplier. Okay, and if I remember correctly, I believe that the multiplier is the bottom one and the multiplicand is the top one. But please correct me if you guys know otherwise. I have it written somewhere. Maybe it's on the PowerPoint of the book. Let's see. Yeah, multiplicand is the top. Oh, yeah, I have them right. Okay, cool. So I do have them. Correct. Okay, and then I guess another term that might be useful is that these things that I did here, the partial steps, are called partial products, and then the final answer of a multiplication is known as the product. Okay, so you know, if you have multiplicand times multiplier is equal to product. Okay, so that's just some terminology for you. Okay, and so if we were multiplying this the old way, let's go ahead and do that. I suppose might as well, since we saw that it was working. That would just be 0, 0, 0, 1, 1, 1, and then you do 0, 1, 1, 1, and then technically you have 2 more lines here that are just a bunch of zeros. Okay, and then you got to do all these additions together. So you got to add that, and then you got to add that here, and then this becomes a 1 here, and then this becomes a 0, and then a 1 here. And so your final answer is going to be 1, 0, 1, 0, 1, which would be the equivalent of 21. Okay, I suppose, you know, that's probably why people complain about this method, because in the other method, we definitely have to make sure that we remember to cut off the extra digits. You know, we have to keep it the same size as the beginning. So like we don't have any possibility of an overflow, because if we do, things break down. Whereas with Booth method, you know, if you have more bits in your output, which by the way, typically if you took assembly, the result of like multiplication is actually stored in the place that's like twice the size of the what it can keep, although that's floating point. But I suppose that could be one of the problems that people don't like about this. That 0 there is just the issue there. So, but anyways, so you know, that's because here we get zeros here, but that's kind of okay. But anyways, so here's the thing. There's a lot of additions that I'm doing here. Okay, it looks like I'm not doing a lot because we're doing them in our heads, but technically, here I gotta fill this with something so I can do this. So like I can fill it with zeros, and then I'm technically doing this plus this, so that's 1 addition, plus this plus this. So that's 4 additions to do that. And then here, like I'm doing additions with the carry as well. So there's a lot of addition that is happening in there. It's a lot of done in our heads, but if you were to code this and you were to time the number of times you actually have to call like an add function, it would be a lot. It will be a lot of times because every single line is going to require you to do addition, okay? We just don't typically think about it that way when we're doing it in our heads, okay? But there's a lot of little additions that you're doing there. You know, if you're doing something like 10 times 8 in this format like this, you know, I know this is 0 here, and then the next time you do this, it's an 8 there, you know, here. But technically here, you're doing what I would consider to be like 4 little additions here. You're adding the zeros here, okay? And then in this case, there's no, well, I guess there's no carry here. So really you're just doing 2. You're doing an addition there, and then you're doing an addition here, okay? But you have 2 little additions that you're doing there. Now, if there was a carry to this, it's like if this was a 2 here, you know, then this would be 2 times 8 is 16. And then here you could do 8. So, well, there's no carry in that one as well. I would have to make bigger math, which I don't feel like doing. But anyways, you can see that there's a lot of little tiny operations that we typically just do in our heads, like adding carries to things, but that you would have to otherwise do, okay? So, with Booth's algorithm, it's going to reduce a lot the number of computations that we have to do, okay? And the way that it works is, first let me tell you some of the rules that will be used in the algorithm. And the rules are going to be that you're going to look at the multiplier. Is it the multiplier or the multiplicand? It is the multiplier. Yes, it's the multiplier. You're going to look at the multiplier. Hold on. Come back. Dog's back. You're going to look at the multiplier, and you're going to, depending on what the digit it is you're going to be using to multiply, you're going to be performing different operations, okay? And so, for example, let's say that you had a multiplier like this, okay? We'll come back to this example, but just to have all possible cases. Let's say that I have a multiplier that is 0, 0, 0, 1, 1, 1, 1, and 0, okay? So what you're going to do to this is throw in a 0 at the beginning just for reference, okay? Just throw it in for now. And now, start scanning from the end of this line to the beginning of the line, so in this direction, okay? And with that current 0 that you're going to look at, there's 2 scenarios that you could have. Scenario 1, that the next digit you're looking at is the same as the first digit, okay? So that would be if you're looking at a 0, and then you look at a 0 again. Or if you have a 1, and then you look at a 1 again, okay? That's one scenario. The other scenario is that the bits switch. So you go, for example, from a 0 to a 1, or from a 1 to a 0, okay? So in this case, let's go ahead and name those things. So when you have a 0, and then you see a 1, we're gonna call that a subtraction, okay? So basically, from 0 to 1, okay? Now, when you have a 1 and you encounter a 0, that is going to be an addition. Like that. So right now, if we go from here to here, that would be an addition, okay? Whereas from here to here, or sorry, my bad. From here to here would be actually a subtraction. But then from here to here is going to be an addition, okay? And finally, if you have the same thing, so if you have from a 1 to a 1 or from a 0 to a 0, then this is just going to be an arithmetic shift. For any of those. Okay? Now, these are going to come in useful, okay? The idea is that the Booth's algorithm is going to perform fewer additions and potentially subtractions than other methods, okay? And so, let's go ahead and figure out, if we were doing it with this specific case, what we would have to do. Well, we started here, and because we have a 0, then that's just an arithmetic shift. Here, though, that would be from 0 to 1, that would be a subtraction. So here, we'll say AR for arithmetic shift, A for addition, and then S for subtraction. Maybe AD and SU, okay? So this would be a combination of first an AR, and then from 0 to 1 would be a sub. And then from 1 to 1 would just be another AR. And then from 1 to 1 again, it would be an AR. And then 1 to 1 again would be AR. And then from 1 to 0 is going to be an addition. And then for the rest of these would just be ARs. Okay? Now I'm going to tell you what to do for each of these. Okay, but that's kind of what you do. I just want to make sure that you understand what is what. So going back to our example here, let me copy and paste it beneath us here. Did I label this as Boots algorithm, by the way? We'll put it here. Boots algo. Okay? So in this case, we're going to look at the multiplier, and we can put our imaginary 0 here just to remember what we have to do at first. And so in the first case scenario here, we are going to be looking at the change from here to here. Now that's going from 0 to 1. That is a subtraction, right? That's this one right here. So we can even label it here. In fact, let's label them before we even do them, okay? From there, the next thing that we're going to have is going to be from the 1 to another 1. That's just going to be an arithmetic shift. And here, I guess I'll put him here. So 0 to 1, and then 1 to 1. From there, the next one we're going to see is going to go from 1 to 0. Okay? So that's the other case. So from 1 to 0. That is going to be a addition. Okay? And finally, we have from 0 to 0, which is just another arithmetic shift. So actually this one has, this example, the reason I picked it is because it has all 4 cases in it, basically. Okay? So, what do we do for each one? Okay? So, when you have a subtraction, you're going to look at the multiplicand, which is the top one, and you're going to do the 2's complement for it. Okay? So, for subtraction, which again is going from 0 to 1 like that, you are going to take 2's complement. I'll tell you ahead of time what you're going to do for addition, which is basically going from a 1 to a 0. For that one, all you're going to do is you're just going to copy paste the multiplicand into that line. So that's not an operation. It's just literally copy paste. Easy. And so there's no addition, no subtraction. Just copy and paste it. Okay? And just so you remember, that would be, if we call this A and B, we're basically copying A. Okay? So that's the one that you just copy. Finally, we have the arithmetic shift. For a 0 to 0 or a 1 to 1. And for those, it's easy as well. All you're going to put is just a bunch of zeros there. Just throw zeros there. Okay? Either one. Whether it's 0 to 0 or 0 to 1, you just put a bunch of zeros. As you can see, the only one of these operations that requires some brain power is the subtraction, because we got to do the 2's complement. But for addition, it's just copying, and for arithmetic shift, you're just throwing a bunch of zeros in. How many zeros do you throw in? As many as you need, okay? And the reason why I say that is because you typically want to throw in the number of zeros that is twice the number of the digits that you currently have in both the multiplicand and the multiplier. So right now, we have 4 digits in our multiplicand and 4 digits in our multiplier. Therefore, when you go ahead and throw in zeros, you actually want to throw 8 zeros because that would be adding those two numbers together, or twice each of those, okay? Similarly with the arithmetic shift, add in twice the amount. So I guess I'll put it in here. Basically, the length or number of zeros is multiplicand plus multipliers number of zeros, essentially. Okay. Yeah, basically. Would there ever be a scenario where you would need more than that? Let me think for a second. Not really, because think about it this way, okay? When you're doing some math, like multiplication, you know, and you're doing it in the form like this. Let's say that you have something like this, okay? I guess that looks weird, but imagine that the x's stand for some digits in the decimal, binary, whatever. When you're doing your multiplication, you're doing this times this times this times this, right? So your first line will have 4 digits in it. When you do the second one, your second line is also going to have 4 digits in it, right? And so in this scenario here, your answer is at least going to have 5 digits in it, right? But could it have more than that? Well, this multiplication could give you potentially an extra digit, I suppose, but not more than that, because otherwise it just wouldn't be possible. Like, this is actually mathematically kind of tricky to prove, but if you think about it in like the highest possible numbers that you could have in there would be that you would have a 9 times a 9, which is 81, right? And in addition to that, you could have a carryover from the previous value, which no matter how big that is, it would have to be a single digit. And so it could be another 9 that you're adding in. And so that still would only really, would only give you potentially one more digit to do, right? Actually, could we get an extra digit like that? If we have 9 times 9 as the last one here, then you know you can get an 81. But could you have an extra carry that would add in here? Well, whatever it is, it's not going to be enough to change this. So I don't ever think you could get something bigger than that. So you just have to do one more there. So essentially, you can see that that's just basically this plus this, which gives you this. So yeah, you know, I shall leave it to the user to prove why that is the case. How about that? Okay. So anyways, if you don't remember that, just remember just throwing a bunch of zeros and a bunch of ones. Okay. The ones that I'm talking about is with 2's complement, because you'll have to throw in a bunch of leading ones if it's a negative number. Okay. So anyways, back to the example that we have here. Remember what we're trying to do is 7 times 3. Okay, so let's go ahead and actually perform this. So for the subtraction, we got to take 2's complement. Oh, I guess I didn't put which 2's complement you got to take. You take it also on the multiplicand. Okay, so take the 2's complement of the multiplicand. So that's going to be the 2's complement of essentially that. Okay, so that is 1, 0, 0 plus 1. Okay, that's going to be basically your answer, which is 1, 0, 0, 1. Okay, so there you go. Cool. From there, that's it. You're done. You're done with that line of code. So now we can move on to the next line of code. You are going to have to fill in a bunch of extra ones here eventually, but again, if you don't remember how many, you don't have to. But for now, let's just go ahead and throw in twice the amount. Basically, multiplicand plus multiplier. So that would be, we have 4 here, so we can throw in like another 4. Okay, so there you go. Then you get to the arithmetic shift, which is just a bunch of zeros. So just throw in zeros. Again, technically speaking, you start out here because remember you always shift 1 when you multiply. So there you go. I kind of ran out of space at this point, but you know, whatever. Let's just get rid of these for now. So like that, okay? Next, you have an addition. So for the addition, we said that we are going to copy the multiplicand as it is into that line of code. So that's what it says. In fact, here, I'm literally going to copy paste it. So I have this here, and I'm just going to bring it down and move it here. Okay, get rid of the little thing here. Okay. Oh, I see. It's because this thing is like there. That looks nice right now. Okay. And then we've had the final line is just another arithmetic shift, which is just a bunch of zeros. So now that we've done that, we can go ahead and fill in the other digits here. So if there's a 0 here, just extend it with zeros. And if there's a 1, just extend it with ones. That's basic simple rule, okay? Once you do that, you are now ready to perform your addition. And so for this addition here, you can go ahead and just bring that 1 down, bring a 0 down, bring a 1 down, and then 1 plus 1 is 0, gets a 1 there, 1, 1, and then a 1 there. So that becomes a 3, so 1 plus 1 there. And then this becomes a 0, and then 1, which becomes a 0, and then technically you have another 1 here. Okay, but that sort of falls out of that. So you don't keep it, okay? And there you go. This is 21. Versus, did we do it before? I think we did, we erased it. But if you compare this with the other version, technically speaking, there's a lot of more tiny little multiplications that we performed. And in addition to that, actually, how do you perform those multiplications? Think about that, actually. So when we were doing it the other method, you know, we're still, you know, well, you can hard code, I suppose, and say that if it's a 1, copy it down. If it's a 0, don't copy anything down, which is kind of what we're doing here, but this is way betterly optimized. So let's go ahead and do another example, okay? So let's try and doing 7. This is one with a negative number. So 7 times 3, but instead let's do -3, okay? So let's go ahead and do 7 times -3, okay? Actually, well, no, isn't that what they use in the book? No, they don't have that one. No, they do have it in the book. So maybe I should do a different number, because you could probably just look at the book for doing that one. Yeah. Here, in fact, if it's in the book, then it's probably here in one of the pictures. So I can just talk over that, and then we can see. Here we go. So let me go ahead and pull this in. Okay, so here is an example of -20. I guess they have 21 there. Yeah, let's do a different one, because that way we're not just using the same ones in the book. So here we got 7 times -3. And in this case, we have going from 0 to 1. So that's this first one here. Looking at our table here, that 0 to 1 is a subtraction. Then this is an addition. And this is a subtraction again. For the subtraction, we're taking the 2's complement of this. For the addition, we're just copying the value over. For the subtraction, we're taking the 2's complement again. So, and then extending everything. And then we add everything together, which as you can see is going to give you 3 here, which is why you get a 1, and then carry this to a 0, and then 1, which gives you 3, and then so on. So that works, it's fine. Over here, we are doing -7 times 3, in which case here we go from 0 to 1, so that is going to be a subtraction, and then we go from 1 to 1, which is just arithmetic shift, so just a bunch of zeros, and then 1 to 0, which is going to be an addition, right? And so that one is just copying the multiplicand down here. So that's how we get this, and then we just go ahead and do the additions, and there you go. Over here, both two negative numbers, we go ahead and do 0 to 1, which is a subtraction, and then from here we do 1 to 0, which is an addition, then 0 to 1 again, which is subtraction, and then everything else is arithmetic shifts. So it's just leading 0, so you don't even, that's why you don't even put it down here. And then from that, again, when you do the addition, you will see that you do indeed get 21. I'm thinking if maybe the errors get caused with the other version, if you're doing multiplication on two negative values. Maybe that's what happened. Maybe that's what breaks the other one or causes issues. I don't know. That still bothers me. I'll have to go and check it later. But yeah. Long story short, you know, it's difficult to prove. This is a much more efficient way of doing multiplications than trying to do the first method that I showed you, okay? And causes less issues with 2's complement as well. So let's go ahead and just do one more example with a number of our own. Okay, so let's go ahead and, I mean, do you guys have any numbers that you want me to do? For those of you that are watching, is there a specific combination of numbers that you'd like me to show you? If not, then I will just go ahead and throw in some random numbers. 23 times 5. Okay, let's do 23 times 5. So what is 23 in binary? Let's figure that out. So that would be 16 plus, can we do 8 at that point? Yeah, we can do 8 because that would give us oh no, that would be 24 or something. I guess we have to do 4 plus 2 and then plus 1, right? So that's how we would convert that to binary. So essentially we are going to be doing 2 to the 4th, we got 2 to the 3rd, 2 to the 2nd, 2 to the 1st, and 2 to the 0. This of course is 1, 2, 4, 8, and 16. And so we have basically this one, this one, this one, and this one. So this is basically 1, 0, 1, 1, 1. So this is the binary representation of 23 yeah, so 23 in binary is 0, 1, 0, 1, 1, 1. And then the other number was 5. So, and then I guess we'll do the 6 times 9 afterwards. That's kind of trolling. Okay, and then 5 in binary. I could do this thing again, but let's just kind of cut to the chase with that one. That's just going to be 101. So that's 5. I guess might as well convert those while we're at it. So this should be 6. And then 9 in binary is going to be 1001 because 7 will be 111, and then 100 will be 8, and then this will be 9. Okay, so just so we have those ready to go. So we're gonna do 23 times 5. Okay, so basically, let's just go ahead and throw them in. So 1, 0, 1, 1, 1, and then I guess I wonder if that is something that we gotta consider. We wanna at least throw at least a 0 here. Otherwise, it might think it's a negative number. So yeah, and then we get 101. So 101. Okay. For this one, actually, here, just do that. Okay. So I'm just trying to think if we really need that 1 there. We probably should, because again, otherwise it'll think it's negative. Yeah, okay, cool. All right, so we are ready to do that one, and then we are also going to be doing this one. So that would be 110 times 01001. Okay, so these are the two we're going to do. And we can throw in our temporary 0 here to make things easier. And let's go ahead and get started. So first of all, we are going to go, and I guess if you want to have the, oh wow, we were really zoomed in. let's see if we can copy this down and make it really tiny, so we can have it handy dandy, or handy dandy notebook. Okay, so we'll just kind of throw that in there. So, okay, so we're gonna start with by going from 0 to 1 because that's the first thing that's happening here, and that is going to be a subtraction, which is taking 2's complement of the above thing here. And so for that, we are going to make that into a 1, 0, 1, 0, 0, 0, but then this becomes a 1 because we add 1, otherwise it would be 1's complement. And that's it. And then from there, we're going to go from 1 to 0. So to do that, that 1 to 0 is an addition, which just means copy paste, right? Copy paste that multiplicand. So that is a 1, a 1, a 1, a 0, a 1, and a 0. Yep. And then from there, we're going to go from 0 to 1, which is a subtraction, which would be taking the 2's complement of that, which we don't need to do again because we already did up here. So we can just copy paste it like that. I mean, we kind of have to line things up now, but other than that, it's good to go. And then finally, we're going to go from 1 to 0 again. That would be a addition. So that would be to copy the multiplicand there. So yet again, we already have that done. So here we can just put it down here. Just again, make sure that things line up so it doesn't mess our additions up. And for the extra digits, that would be like leading zeros here. The reason I'm not putting them here is because they would just be arithmetic shifts at that point, which would just be a bunch of zeros, which won't change the result. So here's the trick though, so you don't mess things up. You don't just want to fill this in with zeros. That will break this thing. You want to make sure that you extend the same digit over. So this is a 1, so you put a 1 here. This is 0, so you put a 0 here. This is 1, so you put 1s, okay? That is because otherwise things will break. Okay, so make sure that is something that you don't want to screw up. So now over here in the front, you could put zeros, and that's not going to make a difference, you know, if you really want to, but I'm not going to do that. So anyways, let's go ahead and do our addition. So this is a 1, this is a 1, this is a 0, and we carry a 1 over. Ooh, this is fancy. We have like 4 1s, you know, on top of each other. So what is that going to be? That is going to be, why is that happening? That's weird. I guess that's the thing that can happen. So that's actually a 1 0 0. So we're actually carrying a 10 over here. So yeah, that's actually good that we're seeing that, because again, you know, this would be 1 1 1 plus 1, which becomes that. So we can only put one digit here. So that digit is actually going to be a 0. And then the other 2 digits are carried over. So now we're doing 10 plus 1, or not 10, 1 0 plus 1, which becomes 1 1. So we put a 1 here, and now we just carry a 1 over. Okay? Now this becomes even more interesting because we have 5 of these here. So because we have 5 of those, that's actually going to be 101. So we put a 1 here, and we carry over the 1 0 there. Okay? From there, we are going to do 1 0 plus a 1, which is again the 1 1. And carry over just a 1, and we have the same scenario here where we have 1 1 1 1, which is 1 0 0. So we put the 0 and we carry over the 1 0 here, and from there we have 1 plus 1, which is a 0, but we also have the 1 0 there, so it's actually going to be 10 0 plus 1 plus 1, which is actually going to be 1 0 0. So we actually put a 0 here, and we put 10 over like that. Okay, so that's actually a pretty interesting one right there. So yeah, okay. Is this correct? Did we get the right answer? You know, well, we're only taking the number of digits there, so that's 2 4 6 8 10, 2 4 6 8 10. So we're only taking these guys because again we're just adding multiplicand and multiplier. So otherwise that extra 1 at the end would mess things up for us here if we took it, because then it would think of it as a negative number. So it's actually good that we don't have to take that in, because again we have 2 4 6 8 10, 2 4 6 8 10. Yeah, so perfect. So is this correct? Is this actually the value that we were supposed to get? Well, we can find out by seeing if what the answer of 23 times 5 is in decimal by converting this to decimal using our little method that we have been using so far. So this is a 1. Okay, I'll put it beneath so it's easier to see. 1, 1, 0, 0, 1, 1, 1, and the rest are 0, so they don't really matter. We can even erase them, like whatever. And so let's just go ahead and see what this tells us in binary. So that would be 2 to the 6th plus 2 to the 5th plus 2 to the 4th plus 2 to the 1st plus 2 to the 0. That is going to be 1 plus 2 plus 16 plus 32 plus 64. What is that equal to? Well, let's do the easy math first. 2 plus 1 is 3. And then plus 16 would be 19. So 19 plus 32 plus 64. 32 plus 64 is going to be 96. And then 19 plus 96, go on, scroll over here, is basically the same thing as doing 95 plus 20, which would be 115, right? Assuming that we didn't screw up the math, let's see if 23 times, what is this, 6 or 5? 5 is equal to 115. So 5 times 3 is 15. We carry the 1 over. 2 times 5 is 10, plus 1 is 115. So there we go. We didn't do it correctly. So we're good. Yay. Plus, I'll tell the TA maybe to do one more of these tomorrow. And so now let's go ahead and do the other one, the 6 times 9. So let's just go quicker on that one because we're going pretty long here already. We still got to talk about floating point. So for that, we're gonna go from here. Let's bring our little chart down. So 1 to 0 is a subtraction. So let's take 2's complement. So 1, 1, 0, 0, 1. But then when we do the add, then it becomes 1, 0 here. And then from 1 to 0 is going to be to copy the multiplicand. So that is going to be 1, 1, 0, 0, 0. And then from there it's just arithmetic shift. And then so from here to here is just an arithmetic shift. So this time I'll put it just so I don't screw things up. And then from 0 to 1 is going to be a subtraction. So that's the 2's complement. So that is 0, 1, 0, 1, 1. And then from 1 to 0 is going to be an addition, which is to copy the multiplicand. So that will be 0, 1, 1, 0. I am going faster, so hopefully I did not screw that up. Let's go ahead and put the answers. 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1. Okay, so that is our final answer. 1, 0, 1, 0, 1, 0, 1, 1, 0. I'm triggered because I was hoping this would be a 0 because that would look pretty, you know? So, but no. Okay, sad days. How many digits do we have here? We have 2, 4, 5, so total of potentially 10 digits here. So 2, 4, 6, so 2, well, significant digits. So technically because of significant digits, we, oh shoot, wait, we screwed up. We did screw up because we did not extend the numbers down. So we did not extend this, the 2's complement one. So, dang. Yeah. The 2's complement that we did was here. So then we got to extend this with a bunch of 1s. And then the second line here is a, not 2's, oh, but we have a 1 there. Why do we have a 1 there? Oh, that must have been the carry digit that we did. Yeah. So, crap. This all got weirded out. Okay, there we go. It's back to being clean. So let's actually extend things that need to be extended. So, hold on. I already messed up the number of digits here. 0, 1, 2, 3. And then this should be all 1s because of the 2's complement. Okay, yeah. So, yeah. See, that's what happens when you rush. So don't rush when you're doing this in the test. So yeah, okay, let's try that again. 0, 1, and then 1, and then 0, and this becomes a 1, so that will be 3, and then this becomes a 1 here, so this becomes 3 again. Bring that here, that becomes 4, so we get a 10 over. Then this becomes 4 again, so we get a 10 over. And then this becomes 4 again, and then we get a 10 over again. Like that. Okay, so this time it looks good. And again, we want to have 10 digits. So 2, 4, 6, 8, 10. So again, we throw away that 1, otherwise things would get messed up because it become a negative number all of a sudden. And so this time, let's go ahead and figure this out, what this would be in decimal, to see if 6, because 6 times 9 is going to be 53, right? Yeah, I think so. And so is this looks pretty small actually to be 53. So we might have screwed something up here, but we'll find out. Although I don't feel like converting it by hand, so let's just go ahead and check it on the computer. 1 1 0 1 1 0 54. Oh, that is 54. This is 54. Yes. So we actually got it right. We got the binary right. We screwed up the decimal one. That's funny. So yep. Okay. So there you go. That's Booth's algorithm. Less computations. I know this is looks more complicated than the other one, but it's actually easier to implement. Or not easier. It's faster when you implement it in an ALU. So an ALU is going to definitely be using Booth's algorithm for multiplication. Okay. So that's multiplication. Division, I'm not going to talk about. It's quite something. It works. You can do it the same way that you would a normal division. Here, I'll show a picture really fast. You got something here, and then you got a number here, and you got 4 digits here, so look at 4 digits here. It doesn't fit in that, so you go 1 more digit. Now this number is bigger than this number. By how many times? Well, how many times can you fit this here? And I guess to make things easier, you can convert this 1001, oh sorry, 10010 into decimal to see what that number is, and then convert this into decimal to see what that is, and then you will see that it only fits once, but there's a remainder to it, which is why is this? Oh, okay. This is the remainder part right here. Okay, but this was not a partial remainder. Then you get the 00111, which is smaller than this. So you bring the next digit down, so that yet again you can now perform a division on this, but which is still too small actually. No, it's not small because it's a 1, so it's bigger. So how many times does 1110 fit into 1011? Basically 1 time again. And what is the remainder of that? You have to do the subtraction to figure that out. And the remainder of that is just 1, 1. So now how many times does this fit in 1, 1? Well, it's too small. So you bring in the remainder of the digits. Well, you bring in 1 and you check it, but it's still too small. So you bring in another 1. So this is the same type of division that you normally do in like math. It's just, there's no special thing with the binary. It's just you got to convert the steps in binary if you can't picture in your head how many times things fit, which is okay. So anyways, you get the 111. How many times does that fit? It only fits once again. And so you can figure out that the remainder is the 10 because this minus this would give you this. And there you go. That is the result of your division. So yes, there's nothing more to it than that. It's rather straightforward, with a big asterisk next to that, because there is some sort of mental conversion to binary that you got to think about. But again, there's no special fancy algorithm for that. Again, this is going to be okay for unsigned, but when you do signed stuff, then yeah, it becomes a bit of a mess. So let's just go ahead and ignore that part for now. We don't. That's too CPE for us. We don't need to know that much. Okay. The only reason I cover Booth's algorithm is because they covered it in my own 219, so I was like, it's kind of, it seems right to cover it. But yeah, okay. So moving on, the next topic at hand, the next big topic, the last big topic, because then again, like I said, once we once we talk about chapter 12, so we're going to talk about that in like 5 minutes. It's going to be floating point notation. So now the next step is how do we store things that have decimals or fractions and things like that in a computer that can only understand zeros and ones. And so the sort of consensus is using a floating point notation. You know, one of the things that we could do is we could totally keep two like variables. One of them, two integers per se. You know, one of them holds the part that is on the left side of the period, and then another one that holds the part on the right side of the period. That's one way that we could implement and solve this. You know, however, people have come up with a little bit of a smarter way of doing it. You know, if you only want to keep things in one variable. And so the way that floating point notation works, I'm first going to show you the sort of generic way, and then I'll show you the official IEEE standard. And so the idea is simple. When you have a normal integer, you know, you can either keep a single bit here as a signed bit, and then the rest of them actually the numerical representation in binary, or as we've been talking about so far, you can just keep the entire thing in 2's complement, right? That works for integers like whole numbers and whatnot. For a decimal, something with decimals in it, what we're going to do is we're going to convert the number into a scientific notation. So like if I want to keep 2.83 in my computer, what I can do, well, that's already kind of in scientific notation. Fail. Let's say we want to keep 283 in my computer. Okay. What I'm going to do is, if I want to convert that into scientific notation, is I need to have one digit here, one significant digit there, I suppose, and then a period, and then all the rest of the digits here after that. However, because I want this to be actually representing 283, I have to multiply this times a power of 10. In this case, the power here is the representation of how many digits you have to move the period by. So, you know, to be able to move back to 283, it needs to go 2 times. So this becomes 10 times 2. Okay, so that's scientific notation. Similarly, if you have a really tiny number like that, you know, it's easier to represent in scientific notation if we go ahead and say it is 8.1 times 10 to the negative, because it's moving the other way around, and that is going to be 1, 2, 3, 4, 5. So that would be -5. Okay, and so if this 8.1 gets multiplied times -5, you're going to get the above. And so this is what all the people in physics and whatnot like to use to keep track of numbers. Why? Because it eliminates leading zeros that are after the period, because then they're actually relevant. Or vice versa. If you have trailing zeros in a really big number, you know, like let's say you're trying to represent how many bytes are in 1 gigabyte. Okay, so how many bytes are in 1 gigabyte? Well, you know, this will be 6 kilobytes. This will be 6 megabytes, and this will be 6 gigabytes. And let's say we're doing terabytes, then there would be another 3 zeros here. Okay, so that's a big number to write down. Oh crap, you're not even looking at this. Nobody said anything. We can't see the drawing. Why can't I see the tweet chat? My bad. Sorry about that. Oh crap. Why can't I see when you guys are writing messages on the chat? Or could you see the chat and I just maybe totally didn't see it? That could be a possibility. But anyways, sorry about that. Okay, so repeat that again. Let's repeat that again. So let's back up. You know, first of all, integers. So integers you can keep in 2's complement, and it's just going to be a bunch of zeros and ones. And if you have something like a 32-bit, you know, 4 bytes integer or sort of address location, then you can just basically keep 32 zeros and ones together. Okay. Oh, okay, that's why. That's why. So I gotta change that. It's because I don't have the overlay on that. That's why. So yeah, that's why I'm missing. So and that's kind of annoying. So I can probably do that really fast. Twitch chat overlay. copy, paste reference. Okay, say something on chat. Let's see if it works. Actually, I can just type in something. Or test. There you go. Yeah, okay, so now it works. Perfect. Cool. Great, great. That's why I keep missing your messages when you guys are pushing things out. So, yeah. Okay, cool. So, there we go. We fixed that. All right. So, yeah. So, okay. So, integer, you know, you just put the zeros and ones together and you remember that it's actually in 2's complement so that you can then convert it back to decimal when you want to print it out of the screen. Floating point notation, which is used to keep decimals, is a little bit trickier than that. One of the ways that you can do it, which is what I was saying, is you could just keep you could just split this halfway. You know, you could do that, something like that. You could say, okay, I got 32 bits, so maybe have 16 here and 16 here, and this 16 are going to be a number, and that's going to be whatever is on this side. And then over here is going to be whatever is on this side. However, if you have a really big number like this, or you have a really tiny number like that, like the 0.000008, then you're wasting space because this thing is not flexible to take advantage of that. So you want something that floats around depending on your needs. And floating point notation is going to be the answer to that, okay? So the way floating point notation works, to understand it, I want to sort of remind you of how scientific notation works, which is what I was just talking about. So if you have something like 283, and you want to convert into scientific notation, the rules of scientific notation say that you can only have one valid significant digit, and then you have a period, and then you have the remainder digits after the period, and then, so you can shift the period around to the right spot to the original number, you can multiply times 10 to some power. In the case of here, for example, when we want to convert 283 into scientific notation, we got to multiply this times the power of 2, so that 2.83 becomes 283, right? Because that would basically move the period by 2 spots. On the other scenario here, where we have something really tiny, like 0.000081, we convert it into 8.1, and we do times 10 to the negative 5. And the advantage of scientific notation is you don't have to write all these trailing zeros or leading zeros, depending on which method you're using. Obviously, trailing zeros, if they're after a period, are pointless, you know, because like 5.1.000, it's just like you can just get rid of these, right? It's just like you can get rid of a bunch of zeros ahead of a number like that, as long as the period is over here. However, what you cannot get rid of is, for example, the zeros in this here, which is the number of bits, or the number of bytes in a terabyte, or 6 terabytes actually, I suppose, because I have a 6 there. And so here you can't get rid of the leading zero of the trailing zeros because they're actually significant digits. Just like you can't get rid of these are trailing zeros. I think I might have said leading incorrectly. These are leading zeros up here, but you can't get rid of them because they're after the period, right? So scientific notation allows you to get rid of them by putting that power times 10. So for example, this in scientific notation would just be basically a 6.0 times 10 to the 12th, I think. 3, 6, 9, 12. Yeah. This is so much nicer to write than this, right? And then of course in physics and whatnot, you know, there's also the idea of accuracy and to how many digits something is accurate. So, you know, when you're writing your scientific notation, if you're doing some computation that is like 8.59, but you're only really accurate, or maybe 8.554, you're only really accurate up to 1 digit after the decimal, then you would maybe convert this into 8.6 times 10 to the oh, I put a 0 where I meant to put the 0 there, you know, and then this would be something like 1, 2, 3, 4, 5, 6. Okay, like that. And that would also be one of the reasons why they would get rid of some digits like that. But they could also put them in, you know, they could also do something like 8.594 times 10 to the negative 6. Okay, so anyways, that's a little reviewer on scientific notation. Now, we are sort of going to adapt that concept of scientific notation to represent decimals in binary. However, that brings a little bit of a challenge, okay? Because let's talk about decimals in binary, okay? How do I represent the following value in binary? Well, first of all, easy one. How do I represent 1 in binary? Well, just 1, right? How do I represent 3 in binary? 1, 1. Those are not a problem at all. The issue comes like this. How do I represent 3.5 in binary? Okay, one option could be to do something like this: 1, 1, and then 1, 0, 1, right? Because this is actually 5 in binary, and this is 3 in binary. Okay, that's one option. However, this is weird because it's not quite right when you're thinking about math. Like, it just doesn't really work out the way you want it to do. You want to represent this as more of a fraction, because when we think about this in math, the 5 is halfway between our numeric system between the 0 and the 9, okay? So it really means 3.5 means 3.5, right? That's what this converts to, 3.5. And that's because the 5 is, you know, if you look at the range of numbers in the decimal system, you know, this with this, and then this with this, this with this, this with this, and then, you know, this are, well, I suppose sort of in between would be this. But if you get rid of the 0, because that sort of means nothing to it, you know, so if we get rid of this, then we can see that 5 is right in the middle of the system, okay? Ignoring the 0, okay, for now. This is right in between, like that, okay? Similarly, if we're trying to say something like 0.25, which is a quarter, right? That's 1/4. A quarter is represented with 0.25 because if we look at the numeric system, you know, a quarter is actually, like, you know, 1/4 of the way, which if we split the numeric system from 1 to 9, you know, into 4 pieces, they would basically get split like this. This is like some hardcore number theory stuff. But yeah. You can kind of think of it like that, okay? Kind of, okay? Again, the 5 is right in the middle. So it's in between the 2 and the 5. And because it's in between 2 and the 5, to get a quarter of the way, we need to represent that as halfway. So we can use the second significant digit to the right to do that. So that's why we put a 5 there, because it's halfway between the distance of 2 to the 3 within its own range, okay? So this is weird to think about it this way, but that's actually how it works in decimal. And because of that, then this is not the right way to convert it into decimal. You need to convert it thinking about it in terms of fractions, okay? So 3.5 in binary would actually be 11.01. Would it be 01? No, 10. Like that. Okay? Which could also be just be said with without the 0 there. Okay? That would actually be halfway between both digits. Okay? Or similarly, if you wanted to do a quarter of things, like if you wanted to do 0.25, you would do 0.01, because you could think of that as being 1/4, 1/2, 3/4. Oh. And then 0, 0 would be 0/4, I suppose, which is just 0. Okay? So it's a weird system, but it's technically correct. So you need to think in fractions when you're thinking how to convert something into binary when it's a decimal value. Okay, let's do another example. Let's say that we are trying to do I think 0.125. So let's say, for example, we're doing 0.125. What is 125? What would that be in fractions? Well, in fractions, that would be basically 1/8. Okay, so how can we keep track of a range that can do something like 1/8, 2/8, 3/8, 4/8, 5/8, and you can simplify these fractions, but I'm not. 7/8, and then, you know, we could say we have 8/8 per se. Okay, so if we have something like this, you know, in the decimal system, we can say 0.125, 0.25, 0 I suppose, 0.375, yeah, and then 0.5, 0, 0, 0.625, and then 0.750, and then 0.875. Okay, and so if you look at the numeric system, that actually represents in terms of fractions the decimals. Okay, and so yes, you are indeed correct. We could use the following system. So we have 0 as always to be 0, so that represented in all systems the same way. But then we could use 0, 0, 0, 1, 0, and then we could do 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. So yes, we would indeed use the 0, 0, 1 here. So 0.25, or sorry, 0.125 in binary would be 0.001. Okay, so it's a little tricky. Take some time to get used to, but you will see that this is pretty good. If we wanted to do something that was like 6.625 to binary, then that would be 1. So this is a 4, so this becomes 5. So that's 6, yeah. And then 625 would actually, oh, interestingly enough, it would be that way. Oh no, sorry, 101. My apologies. There we go. Okay. I looked at the wrong column here. 625 is this one. There's a different color maybe. Red is like a sign of no, but here it's like a sign of yes. So yes. Okay. So okay. Assuming that you got that part so far. Now what we want to do is we want to convert the decimal value that we want to keep. So let's say we want to actually keep this in a floating point notation. So 1/2 is 0.1, 1/4 is 0.01, 1.116. Yes, and that's actually very important to actually think about it that way. So I'm glad that you put it out like that, because that's actually going to come into play with floating point notations and how we can sort of hold that data in there. So yes, they're all fractions. The more zeros you add, the more one fraction of power of 2 it is. So then it will go to 1/32nd, 1/64th, 1/28, and so on. And what you'll find out is that floating point notation is just kept as a bunch of fractions that you add together to find out. Because here's the thing. If you want to convert, so how do you convert? Let's talk about that. That's actually something useful. I have it in my notes, but that's actually a kind of useful thing to know. How do you convert it back? So how do you convert it back into decimal? So you use the same system that we had before. So like if you have the following, so let's just say we have 0.10001. Okay, I don't know what this is in fraction, okay? But it's some fraction there. So what you can do is you can use the same system that we had here, but backwards. So you have 2 to the 0, 2 to the 1, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, 2 to the 5th, 2 to the 6th, okay? And so we know that this is equal to 1, 2, 4. Well, here, let me put them on the top because I can do something to them. So let me put some space here. So this becomes 1, 2, 4, 8, 16, 32, 64. And now the difference being with the fractions that I'm just going to throw a 1 in front of them like that. Okay? And I'm also going to sort of kind of get rid of this first one here. Okay? So now, if I want to figure out what this number is, I can just put it right here. So 1, 0, 1, 0, 0, 1. And the result of this is I'm going to pull down the ones that have 1s attached to them. So that would be the 1/2. By the way, so that this makes more sense to you, let me go ahead and actually do the same thing with these values. So these are all over 1s. that. So this becomes 1/2 plus 1/8 plus 1/64. And so what is that equal to? Well, 1/2 is equal to 4/8. So 4/8 plus 1/8 is 5/8. And then what is that in 64ths? Multiply times 8. So 5 times 8 is 40. So 40 64ths plus 1/64 is 41 64ths. Now, what is that in decimal? What is that equal to? 23, 0. 4 times 5 is 20. So that would be 205 minus 230. That would be 25. Throw in a 0 here. And then again, this would be 4 times 5, 4 times 6 this time. Close enough. So let's go ahead and put in 0 here. So this is approximately 0.0156. Did you guys put somebody do it on YouTube? What is 41 divided by 64? That does not look right. I screwed up. Oh, I think that does not look right. 41 divided by 64 is, that number should be like over half. Oh. Fail. Epic fail. I put the things in the wrong order. 64 divided by 41. Omega low. So, yeah, I flipped them. But okay. I got 0.64 0625. Okay? So, which is just over half. And that does seem about right because we have a 1 here, so it should be over half. So, yeah. If we were trying to keep this number in decimal, in binary, we would keep it like this, which is basically a bunch of fractions added together. So that's exactly how floating point notation is kept, as a bunch of fractions that you use to add together to come up with a number. That is why it's also, as you can kind of guess, some of these might be irrational numbers potentially. So that is why you can't sometimes keep certain numbers precisely in floating point. For that, I have a little example to show you. Not this one. This one. Okay. So here we have a little bit of C++ code. We're using the IOMAN IP library so that we don't see scientific notation and we actually see decimal digits. If you don't remember that, you can just watch one of my lectures on 135. We use the fixed keyword along with set precision so that we can see the decimal value of this. Even though this doesn't have a decimal value to it, it's a whole number, but otherwise the scientific notation hides that. So we are assigning here a number, which by the way, this is technically assigning it a double, but we could assign it an integer by getting rid of the 0.000 here, and we get the same situation. But we're assigning it a number here into y, okay? And then we're going to go ahead and print out what is in y right here, okay? And just so the output looks nice, we're also printing it out again on top. We should expect to have the same number, right? We expect y to hold the number 33,554,431, okay? But you know, there's a reason I'm showing you this, because you can probably expect something weird is going to happen here. And that weird is that if I run this, oh, wait, where did it go? I knew it, that's why I Control-C it, because I knew that would do that sometimes. If I run it, I see that I'm not getting the same number. I am getting a 31 and a 32. Yeah. See, this has happened before to me when I was. This ID1 is what I use when we're actually teaching in Pearson 202, and I don't want to have to bring a laptop to the classrooms and they're running Windows. And it has happened to me before where I will type in code, I hit run, and the thing just disappears because there's a timer or something. And so I always control C it because I know this will happen. Like I've been traumatized into remembering. So yeah. So as you can see, it's not equal. And the reason why is because when the floating point notation is doing all these fractions to keep track of this, there isn't a certain fraction addition that it can do that it can give you the exact number. And it's actually off by one whole number. Now, if I throw in an F here, just so you don't think like, oh, okay, well, it's kind of related to the double and float thing, it's still going to give us the same issue here. Because, you know, technically without the F here, this was a double, and then they got coerced into a float. But if I put the F there, then it has always been a float. So there's no suspicious thing going on there. I can also just do it as an integer, like that, and it'll also give me the same error. Not error, but, well, technically it's an error, even though it's a numerical error, right? And so that's a problem. That's a very serious problem because, like, this is one of the reasons why one of the ships that went to Mars crashed, because they screwed up numerical conversions. And I think there has been another ship that has crashed because of a floating point error as well. We can probably Google that very quickly here. Floating point error ship crash. A floating point error that cost a damage worth $500 million. The story of Ariane 5. The maiden flight of Ariane 5 launch ended in failure. And what exactly happened? A 64-bit floating point number relating to the horizontal velocity of the rocket with respect to the platform was converted to a 16-bit integer. The number was larger, well, in this case, I guess it was an overflow. The largest integer storable is, thus the conversion failed. So I guess in this case, they try to convert a really big number into integers, so it overflowed. But yeah, anyways, still related to floating points. And I think there's another example as well. But there, disasters due to rounding error. Oh, that's just an example, I think. But there has been cases like this, okay? It's very, very popular thing to make numerical errors. And so you can't just trust your life to floating points, especially not float, but doubles are probably a better chance, but still. Because the numbers are represented as a set of fraction additions. They're all fraction additions, and that's all they are. Here, I'm going to copy this in case you want to run it yourself in your own IDE, in case you don't trust me. If you think I did some black magic to the code, you know, you can go and experiment on your own. Just click on that link, and it will open this up. Obviously, it's not the same one, so I won't see your changes. That'd be kind of cool, actually. But yeah, so it's just a bunch of fraction additions. It's basically me trying to just add as many fractions together to get as close to the number as possible. And it turns out that it's a very hard thing to do. And it's very, very difficult and not easy to do. Like, for example, something as trivial as 0.75. If I want to represent... Actually, well 0.75 is not the best case scenario. If I want to represent something in between a third, let's say I want to represent 1/3. Yeah, 1/3 is good. These are all powers of 2s. And we know that 1/3 is a number that's, you know, I suppose, I guess it's considered a irrational number because it doesn't end. It just goes on forever, right? 0.333 forever. No matter what magic you do here with fractions, it's going to be very tricky to basically be able to come up with an actual representation of 1/3. And so that becomes a problem, even with such a basic number. And there's no solution to that. So that's just introducing to you. Now, how did they actually keep these fractions in floating point notation? Let me show that. That is actually quite trivial. The hard part is understanding the fraction stuff. So the original version of it is, you know, remember, there's 32 bits typically used in an integer. So we're going to stick with a 32-bit count. And what you do is you split them into 3 parts. You have what is known as the significant bit, which is called the sign of the significant, or if you are an old person, you would call it the mantis. Significant. I'm not intending that to be offensive, but it literally says down here, the term mantissa, sometimes used instead of significant, is considered obsolete. Mantissa also means the fractional part of a logarithm, so it's best to be avoided in this context. So it's an outdated term apparently. So I guess that's the thing. So in case you won't know, it's spelled Mantissa like that. So yes, it's old. So anyways, the sign of the significant bit is stored there. So that's just a 0 or a 1 if it's a positive or negative number. This is not 2's complement. This is just like the most basic sense. If it's a 0, it's positive. If it's a 1, it's negative. So remember, this is 32 bits. So that's 1 bit there. The next 8 bits are going to be what is known as your exponent. But it's not just any kind of exponent. It's called biased exponent. That does make things a little trickier, but it's something quite trivial once I get there. And then the remainder of the bits, again, in the old days would be called the mantis, but now it's just called the significand. Okay? And these are going to be 23 bits because this is 8 bits long. And this all, as you see, adds up to 32 bits. Okay? Or it should, actually. Yeah, it does. Sorry. The math failed me for a second. I thought I was doing 34, but I was doing the wrong math. Okay? So, yeah. So obviously, one of the easy ways that you could do this, if you were trying to make your own floating point, is you could keep this significant, like we were saying before, as just an integer, right? And then you could use and that would be perfect if you wanted to keep something like 0.223, then you could just make the integer be a lot of 3's in there, as many as you can fit in there. But the reality of things is that the significant is kept as fractions that you're seeing here. So it's kept. So the values here is what is being kept in the significand. And furthermore than that, it's actually kept as scientific notation. So let's imagine a floating point world where we are keeping decimals in here. So if we were keeping the value of 283, we know that the scientific notation of that is 2.83 times 10 to the second. The way that you would keep this here would be a 0 because it's a positive number, a 2 in the exponent side. Again, we haven't talked about what the biased part is, but if it wasn't biased, and then the significant would have a 283, okay? Or, just so you see the difference, let's say this is a 483, okay? Just so I don't want you to get confused between this 2 and this 2. So this becomes a 4.83, okay? So then this would be a 4 here, okay? That would be sort of the equivalent if things were in decimal, but they're kept in binary because you can because every computer's in binary, and also you can do a little trick to gain an extra bit. So let's go ahead. Dog is being toxic. Let's go ahead and store the one that we just did here in the computer, okay? Yeah. Oh, I didn't copy it, I think. So this value here, copy. Oh, and by the way, I wanted to point something out about this. The 0.101 here is close to the 0.101 here, which was 625. So it does make sense that this is actually a little bit over, like a little bit 64, a little bit over 6264 because of that. So yeah. But anyways, I don't think she's hungry. She ate way too much food already. So anyways, let's go ahead and say that we are keeping a little bit. Let's put some more digits here so that like ahead of this. So maybe we want to put in like a 1001 in there, okay? Yeah, 1101, okay, like that. So the way you're going to store this in your floating point notation is you're going to convert it into scientific notation by moving the dot to the left until you get to the first significant value. So it becomes 1.1001101001 like that. And technically here, because it's binary, your it's not times 10. I think it's times, well, it would be 2, but 2 in binary is 10. So you are putting a 10 here, but beware of that. It's not a 10, it's a 2, okay? It's 2 in binary. So it's kind of weird about that. So yeah, so how many digits did we move it here? We went 1, 2, 3, 4. 4 in binary would be 1, 0, 0. Okay, so be aware about that. You're doing times. It looks like you're doing times 10, but the reality of things is that it's really 2 to the 4th. But I'm just putting it in the binary representation of that. Okay, so yeah. Don't freak out. You're not moving. It's not times. It's 10 to the 100th power. It's actually just 2 to the 4th power. Okay, so what you do, in fact. Here, let me just copy paste this so I can just fill it in. This is a positive number. So first of all, for the for the sign bit, we are going to put in there a 0. Let me go ahead and fill the significand first. The significand is just going to be the 1, 0, 0, and again, this is going to be optimized in a second here. There's a little trick we're going to do. 1, oh, well, we forgot the 1 there. So 1, 1, 0, 0, 1, 1, 0, 1, 1. Yeah, it's right. I said it wrong, but it's right. And then the power is a 4, which is just a 1, 0, 0. Okay? However, technically speaking, we expect 8 bits here, so we would just basically throw in leading zeros. So we have 1, 2, 3, 4, 5, 6, 7, 2, 4. Shoot. Let me make them smaller. 1, 2, 3, 4, 5, 6, 7, 8. Okay, there we go. And then because we expect 23 bits here, we have 2, 4, 6, 8, 10, 11. 12, 13, 14, 15, 16, whatever, until you get to 23. Okay. The reason why is because again, that way it's just one continuous flow of numbers. Otherwise, you need to make sure you know where the exponent ends and the significand starts, right? And the way you know that is because you count the number of bits. That's why you don't just do 0 like 0, 1, 0, 0, and then start putting these guys in, because then you wouldn't be able to separate them. So that's why you fill it with extra zeros. But there's 2 things that we have to do here to make this correct, or floating point proper. First thing is, because I don't really know the true reason as to why the bias is done the way it's done. I guess it's because they want to. I don't know. I really don't. That's something that you're gonna have to. I don't even think it's mentioned in the book, but for some reason that. Probably smarter people that came up with this thought it was actually a good reason. The exponent doesn't start from 0. Probably the reason why is because they didn't want to do 2's complement here, and so the range of 8 bits can cover from 0 to 255 if it's unsigned. If it was signed using 2's complement or whatever, then you could cover from like -127 to probably +128. Okay. However, instead of storing this in 2's complement, they decided to store it unsigned, but to be able to store, I guess, negative numbers, there's a bias. If you have all zeros into the exponent, so 2, 4, 6, 8, then that actually is considered to be -127. So all zeros is -127, and then if you had like that, which is all zeros but 1, this would be -126. So the formula for this is that the bias is equal to 2 to the 7th minus 1, or can also be considered as 127 basically, which is equal to 127. Because 2 to the 7 is 128, and then minus 1 is 127. So that's the bias, okay? So because we're trying to represent a 4 here, what we end up having to put in here is would be 131 in binary, okay? Because that would actually be the representation of 2 to the 4th, okay? Again, if it was 127, that would be the representation of 2 to the 0. The reason again for this is because they want to be able to keep a range of positive and negative exponents, but they didn't want to use 2's complement. Again, don't ask me why they chose to do it that way. They just did. And so because of that, this isn't represented actually as as 000100. It's actually represented as whatever it is in binary to do 131. So for that, I'm going to turn over to my calculator here so that I can say enter decimal to binary 131. So that is basically a 1. Oh, here, let me use the same color. So we're trying to put in here 131 because that is equal to basically 127 plus 4. Okay, and so that is 1, and then there is 5 zeros there. So 1, 2, 3, 4, 5, and then 2 ones. Okay, and so that is basically going to be the exponent that represents 2 to the 4th power because of the bias. Okay, finally, there is one optimization that we can do here because in binary there's only 2 symbols, 0 or 1, and 0 is basically useless in scientific notation, right? There's never a situation in scientific notation where we would have something like this times 10, or again 2 to the some power. You know, if we have something like this is bad because, or well, I guess, sorry, this is binary, so no 2. So this is bad because we could probably move the dot here. So there's never ever a situation, or for example, if we have something like this, that 0.1, because yet again, we could go ahead and move the period here. Okay, so there is never ever a situation where you have a leading 0 in your scientific notation. In any number system, even in decimal, you will never see scientific notation start with a 0. Because the whole point of scientific notation is to get 0 zeros. However, in the decimal system, it could start with anything from a 1 to a 9, just not a 0. Okay? However, because in binary there's only 2 symbols, what do you think it's always going to start with? A 1. Because of that, because we know that it's always going to start with a 1, we can get rid of it. And why is that? Because we know that when it comes time to actually write this down into the equivalent representation, we will add it in. We'll always add it in. And because we can always add it in, we can get rid of it. And by getting rid of it, we have 1 extra bit that we can basically use to store actual data on. So it's a little optimization that you do when you know that little trick. It's a little trick to add an extra fraction in there, so to have higher accuracy. And that's pretty much how floating point notation works. That's all there's to it. There is a little bit of a downside to this that I want to talk about, and then I want to talk about doubles, which will take us like 5 minutes as well. So we're almost done, and it has been a long lecture, so probably I will like make a really short lecture on Monday or something to make up for it, or just no lecture on Monday or something. I don't know, since the lectures have been quite long recently. But if we look at the PowerPoint, there is a little interesting thing that happens here. Yeah, this one. Because of the way the fractions work, you get a lot of little tiny fractions, right? And this actually happens with scientific notation too. In regular scientific notation, like in decimal values, you can keep, let's say that I told you that you're limited to only storing 5 digits, okay? So you can do like 5.4445, okay? 5 digits, but you can't have more. Your exponent can be anywhere from like 0 to 100. So you can keep a broad range of numbers, right? You can keep somewhere from like super tiny values, because if you do like a negative 100 exponent, to really big values if you do positive 100 exponent, right? However, the bigger you go, the bigger of gaps you have between values. Because if you do something like, oh, no, that's not a good idea. Let me actually switch. Yeah, if you do something like this, you know, if you want to keep, for example, let's say you're keeping, let's say that you're limited to 3 digits, okay, just to make this easier. You could keep something very accurately from anywhere from negative, basically 999 to positive 999 if you can keep 3 digits in there. However, if you're trying to keep the number 10,000, you know, you can do that 100% accurately. But what you can't do is keep 1001 accurately, because when you try to convert that into scientific notation, it becomes 1.0001, but you can't keep more than 3 digits, right? And so you lose these. So if you were to chart out the range of numbers you can keep a lot of really tiny numbers, you know, accurately, because you can do something like 0.000, 100 zeros, and then have like 111 there. You could do that. But then, you know, the next gap of numbers that you could keep would be like if you get rid of a 0. But you miss out on a lot of numbers. So ultimately, let's look at the positive numbers, you know. When you go from 999, the next number that you can keep in there is going to be 1,000, you know. And then from 1,000, you can keep up to like, you can go all the way to 1,000. You can go all the way to 1,010. You can't keep anywhere from 1,001 to 1,009 because that would include this digit, which would mean you can't do the scientific notation properly. So the range of numbers would be like this. Would be 999. Anything include all numbers from 0 to 999 included. But when you get to 1,000, you can keep that in because that just becomes 1.0. And just becomes 9.99. But from there, the next number that you can keep is 1,010. Because if this was a, like, let's say 1,005, you can't do this with 3 digits in scientific notation. You will need the 4th one for that. So otherwise you lose the accuracy. So you can't keep that. It's going to be lost. The next number you can keep is that. And then you can keep going in increments of 10. And basically you can keep doing that system all the way until you get to that number. So you're going to be able to keep, you know, 1,020, 1,030, 1,040, 1,450, 1,460, and so on. When you get to this, actually this will work all the way until you get to 9,990. So you'll be able to keep it in increments of 10. But then when you get to 10,000, now you can't do 10,010 because again, this is 4 digits. So from there, the next number you can actually keep accurately is 10,100, and then 10,200, and 10,300. And you basically have 100 numbers there that you can't keep because you lose accuracy in those if you're limited just to 3 significant numbers. And this is going to be the same system that you're going to be going like this until you get to 99,900. From there, when you get to 100,000, you can keep that accurately, no problem. But then from there, the next number you can keep is 101,000. And then 102,000. And so now you're going in ranges of 1,000. So as you can see, that is what this chart is sort of doing. It's going, you can keep a lot of tiny numbers, but the bigger the number you go, the bigger the gaps between the numbers that you can actually keep are. Like, you start out with the small numbers, like you can keep everywhere from 0 to 99 in our example. And then from there, you start going in jumps of 10s, and then you go in jumps of 100, and then jumps of 1,000, and then jumps in 10,000, and so on. And so that's one of the problems with floating point notation in the way that we're doing it with the significant. Because remember, the significant means that you can keep up to 23 significant digits. In my example that I just gave you with decimals, it was 3 digits. But so you can keep a lot more accuracy with 23 of them in binary. However, you know, the same issue will happen there. It's just not going to happen faster enough. But eventually it's going to happen. And eventually it's going to be a big difference, like 1,000 numbers between one or the other, okay? So it is going to definitely happen. It's just going to take longer time to appear, or a bigger range of numbers. But it will happen. The same thing happens if you go the other way around to smaller digits like fractions, because again, you're not going to be, you know, if you have those leading zeros, if you got 0.1 and then you got 0.000 at 5, you're not going to keep that 5 at the end there. It's just not going to happen. However, the system of fractions does help you with that. But and this, of course, will happen with positive and negative numbers because the sign bit will the same issue will happen. So in our system here with the decimals, we wouldn't be able to, we would be able to keep -10, -20, -30, or sorry, -1,010, -1,020, -1,030. We were able to do that, but we still would have to eventually go on to -10,100, -10,200, -10,300. So same problem, okay? Positive or negative. There's no solution to that, actually. It's just a limitation of the ranges. You can't just create information out of nowhere. With integers, you can keep full accuracy, whole numbers, you know, from like negative 2 billion to positive 2 billion, or if it's unsigned, from 0 to 4 billion. But that's, again, because that's the number of digits that you can hold with decimal values that you can hold with 32 bits in binary, right? Floating point, you can hold a bigger range of numbers with that, but you're still limited by the fact that you're only having 32 bits of information. And so the only solution to being more accurate and to sort of fixing this issue is just to have more bits in the significant part. And that's what a double is. A double is going to be basically the same thing. It's just more bits on each of the pieces. And so rather than me drawing it, let me just show it to you here. So IEEE 754 format is the official floating point system that is like the universal system that is used in the computer. And for a 32-bit system, a floating point is going to be 1 bit for the sign bit, because you never need more than that. 8 bits for the biased exponent, again, with a bias of 127. And then the significant field, which is the mantis, if you want to call it that way, is 23 bits for a float. And then for a double, I think this would be a double with this, at least in the old days, a double would be 1 bit here for the significant again. You got a little bit more on the exponent. You can go up to 11. So that means that if this is if this is from 0 to 255, then this would be 512, 1024, 2048. So from 0 to 2048. And for that one, I think the bias is still 127, even though you are you have a bigger range. I can double check on that very quickly here. What is the bias when you go to like a double? Let's see. You can probably Google that actually and find it faster than I can look it up in the book. Oh, there's a chart on the next page. Yeah, there's this chart. So the bias, the bias does change. The bias is now 1023, sorry. So the reason, what that means is that the range of exponents goes from negative 22. So it's always in the middle, I suppose. Again, I don't know why they chose to do the bias system instead of using 2's complement. I'm not 100% sure why they did that. They just chose it that way. Again, this is a standard that was universally accepted, and now we're stuck with it. And then when the 64 version came out, it was just the same people didn't want to change the idea. They just want to expand it upon it. So they kept the same system of a bias. And now we have the 128, which I don't know when it's actually used, because as far as I know, this is more of a double and this is a float. A double being, they say double accuracy, but it's not exactly double accuracy, because you can see you go from 23 bits to 52 bits, which is a little bit more of accuracy than just doubling it. But the range of numbers is greater, so yeah, it's iffy. But yeah, that's basically how IEEE standard goes. You know how to convert things now for the significant. You got to do the whole fraction math, or do the 1 divided by the 2 to the power conversion. And then you know how the significant works with the bias. Again, it's unsigned addition, but then do the biasing. So again, if you have a power of 4 and you were doing this system, then you know that the bias is 1023. So that would mean that the number you need to put in here would be 1023 plus 4. So that would be 1027. And that would be the number in binary that you would keep in there. So what does that actually look like? They have an example here with numbers, which again is kind of what I put to you. So you got your sign bits, and then you got your exponent biased, and then you got the digits here in the fraction, I suppose. And then here's this. Oh, is that almost look like the one that we did? That is not intentional. Was that the exact number? That would be scary. No, it's not. Ours was 100. That one's 101. So almost, though. You can see it's kind of close because ours is 0.64 something and this is 0.63. But you can see there's a lot of leading zeros here that they fill in just to, because you always want to have it to be the size that is expected. Although, again, this does mean that you're pretty successful at being accurate. When you're not accurate at this, when you know that you lost some accuracy with this system, is when there's at least a 1 here or a great or there's all 1s here. But ideally, if you see a 1 here, then you may have lost accuracy, because this is basically the smallest fraction that you can add. This is 1 divided by 2 to the I'm gonna guess 2 to the 22nd power. So that's a pretty small number. 1 divided by 2 to the 22nd is 2 to the scientific notation of 7, so that would be 1. It's less than 1 millionth. Okay, it's less than 1 millionth of a value, so that's super tiny. Okay, and if you're adding that in, it means that you're trying to come up with some really weird number, and more than likely that's because, again, you can't have the exact representation. I do know, by the way, this is just a fun fact that maybe you learned in 218, that when you're doing register multiplication and division, or you're just dealing in general with floating points, you have a special register that keeps twice the size temporarily before storing the final answer, and maybe that's what they're using the bottom one here for, this one. So yeah. So yeah, that's pretty much the chapter. That's all I want to cover of the chapter. You can read the rest on your own leisure. There is some really complicated stuff about how to do floating point arithmetic. It's not easy at all, like integer arithmetic. There's this sort of logical chart that you have to follow to figure out how to do it. I guess one thing that I should point out is how do you detect a 0, or how do you store a 0 in floating point? Because remember, we're doing that little trick to have one extra bit, but because we know that it's always going to be the case that we have a leading 1 in the scientific notation representation. So because of that, the only case where that is not true is if the number we're storing is a 0. That doesn't have a leading 1 in front of it. So how do we actually know that that's actually a 0 if we can't do that? Because it's always going to add a 1 to it. And so it turns out that it's a special case where you want to store here, I have it here. Basically, I think you store 0 in the exponent, and then you store 0 in the significand as well. I recall there being a chart here that told us special cases. Here, this one. So, a positive 0 is a sine of 0, a bias exponent of 0, and nothing on the fraction tier. And obviously that gives you a value of 0. And there is such a thing as a negative 0 if you switch the sign bit to a 1. So, whatever. We just deal with it. I guess that's one of the reasons why they might not be using the 2's complement for the exponent, because that way they can have a special situation for 0 inside of that. Otherwise, that wouldn't really work out what they're doing here. So, because again, the other scenario they could have is what if you just want to store 1 in your floating point value? 1. The fraction system for that, you know, you really would just have like what? You wouldn't have anything there. You have zeros there because of the leading 1, right? So it would be an exponent of 0, and then 0 in the significand because of the added 1. So then that would be a problem, right? So how would you store the 1? So yeah, that's the reason why they do this method here like this. So anyways, there's also another nice thing. You can store infinity per se, and what you do is you put all 1s in the bias exponent, and then you keep the sign as 0. Or I guess you do, well, 0 for positive infinity, 1 for negative infinity, and then 0 in the fraction. And then there's some special ones as well for like not a number and whatnot. So yeah, there's some other it's just part of the standard, and so you can look at that on your own time. But like I said, this of course is beyond the scope of us. But if you want to go hardcore, you can read into the detail of how to do the floating point addition, subtraction, multiplication, and division. It's not trivial. Again, it's an algorithm that you follow. This is basically, you follow this sort of quiz chart and it tells you what to do. But it's not simple at all. So I'm not going to ask you that on the test, but it's interesting, you know. It's just interesting to learn, and then you just forget it. At some point I knew it, now it's just gone. So yeah. Anyways, that's the chapter. That's chapter 11. And so now, very briefly, let's just look at chapter 12 so that we can call it a week. And so if there are any questions, let me know, by the way. So chapter 12 is just Boolean algebra, which again, is CP 100, you should know. I mean, like literally, it's like the truth tables. So, you know, and, or, not, you know all of this already. NAND and NOR, if you don't remember those, there's this refresher. Really the one that we like have been using is XOR when we're using with Hamming code and things like that, bit parity checking and whatnot. That's exclusive OR, but you know, NAND is also nice. It's like the opposite. So basically, the opposite of NAND, or the inverse of it, is NAND. And the way that you can get that out of this one is you can just feed it through a NOT. So basically, with the and, the or, and the NOT gates, you can mix them up and you get the other truth tables that you're getting here. So like NAND is basically an AND gate with a NOT at the end of it, after the output of that. The XOR, on the other hand, is I think I showed that the other day. I think it was one of the inputs you flip, and then you feed them both through ANDs, and then you OR them out together at the end. So yeah, I think that's how you do the XOR. Again, refer to that video for that one. The NOR is just the opposite of AND, so you can just, sorry, the opposite of OR. So you can feed an OR and then just feed it through a NOT gate, and then you get the NOR. So yeah, again, this should all be relatively reviewed from CPE 100. Some properties of this, and these, you know, I didn't remember them, so now we do. How to actually draw them. So the XOR, it looks like the OR, like the OR, but you have the second line and so on. You have questions. So participation discussion is all only on Fridays with the TA. From now on, starting tomorrow, yes, it will be basically he will record the participation, and then that will be it. I haven't decided if the Thursday before the test, because your test is on a Friday, if that day is going to be a TA day, because then he can do some review with you, or if I will do that myself. But either whoever does it, I think we will do it live, because that will actually help you. So expect next Thursday to be live, so that you can do a review for the test. So yeah, but Monday, Tuesday, Wednesday to next week, we will just do remote. I mean, I might record it and go live, but it depends. I don't know. This stuff I thought would be useful because I thought you guys would have more questions, to be honest. But yeah, so yeah, that's pretty much what this chapter is. They do talk about flip-flops, which you have talked about already. Here's some implementations of some basic things, like mathematical things, like sums and whatnot. Cardinal maps we don't have to worry about. Hopefully you learn them in CPE. Here's an AND implementation. Basically feeding in the result, but you take the knots. That's what that little line means there. Multiplexers. It's been a while with multiplexers. Yeah, that has been quite a while for multiplexers. I just go ahead and read through that, and I'm not gonna ask you pretty much anything from this chapter probably in the test, but I still think it's a good review. Multiplexers connect multiple inputs to a single output. At any time, one of the inputs is selected. So, yeah, that does ring a bell. Then they have an example of a ROM. So that's nice. And, oh, here's an adder. So I'm sure that we all, at some point, did an adder in a breadboard. I do hope that you guys did that at some point. It's cool. It's nice. But really, the point of doing it is to just understand that you can convert any mathematical operation into just logic gates, which is how your CPUs are made with a bunch of transistors. Everything is converted into logic gates. So, yeah, that's really the purpose of that class. So, yeah, that's pretty much it. Here's a flip-flop, I guess. I think I might have shown you this before, but this, you know, is how you can implement really fast memory, because you can do this at the CPU level instead of doing it outside, you know, because remember, RAM is done with capacitors, which leak memory and things like leak electricity. So, yeah, but like I said, you know, this is all CPE. Oh, there's FPGAs. I think I might have showed you guys. I did a little slot machine with an FPGA as a project in CPE 100. So yeah, but those are, yeah, I guess field programmable gate arrays. So they allow you to sort of prototype a some potential logic array that you might want to like eventually implement, you know. So yeah, it was fun. It was fun, but it's definitely burdensome to do that. I mean, especially because like the one that I implemented, I did it drawing the actual diagrams. Like I did this stuff, and so there was like 200 of these logic gates that I had to manually hook up together, and that was not fun. I have a video on YouTube about that. You can just go on my channel and look at like FPG, like DE2, because that was the name of the board, slot machine or something. And then at some point I put the camera very briefly to show the logic, and God, it's just scary. I want to pull a picture of that now. So floating point stuff was covered in 218. Yeah, I personally remember 218 covering floating point. But however, at the same time, I wanted to make sure that I covered it because even though it's covered in 218, and I'm happy for that, it's technically more of a 219 thing. But you kind of need it in 218 to understand what the heck is happening at the assembly level. So like I understand why like Ed and Brian usually would cover that. Here, just want to show you the horrifying thing. I mean, it's cool stuff, but it's just so burdensome. So, if I go at the end, well, here, if you push it, you can see that it starts spinning and whatnot. So there's a spinning, and then if you manage to win, it would make all the lights go crazy and whatnot. There I'm showing a test, but you can watch this on your own. But anyways, just look at this and you know, cringe. Yeah. All done by hand. So, you know, been there, done that. Don't want to go there again. And there's more. Yeah, I scroll down through this all. So, yeah. You know, fun times indeed. So, yes. You can check that out on your own time. And of course you get the people that are trying to like cheap fry for their own classes. They're like, hey, can I look at your code? You know, can you send me the project? Because they want to use it in their own class. I mean, like, I don't even have this anymore. I burned it afterwards. So yeah. Okay. Didn't want to even keep it. But anyways, that's the class. That concludes CPE 100 day in CS 219. The rest of the class is a lot easier. we just talk more about stuff. No more hardcore math, and so on. So yeah, this was a long video. By the way, it's gonna take me like 2 days to upload it probably now. But at least now it's available on Twitch. So people can watch it on Twitch immediately after I finish. So they can watch it then. And I will go ahead and make the lectures next week extra short, or just not have a lecture one day, because at this point you guys have watched this week like 5 hours worth of lectures, and in like 2 days or 3 days, you know. So yeah. So yes, and for those of you that came from other places like 202, then hey, you might have got an extra credit if you were here for that, because I am using Twitch for the 202 class, and that's how they don't have participation points, they have extra credit points. And then random people also came. Well, not random people, but people that eventually, I suppose, will take 219 if they haven't already. So, okay then. I'm gonna go end now and take a break before my 202 class later today. So, hope you learned a lot, you know. It's interesting stuff to cover for sure. Brings up some interesting memories as well. So until then, have a great weekend. In 219, make sure you work on your project. And then yeah, this is definitely some interesting stuff. But hey, if you're in 202 and you saw this, you might actually have a better understanding of floating point now. And when you do get to 218, then it'll make more sense too. So yeah, cool. All right then. Well, thanks for watching. And if you're in 219, have a good weekend. If you're in 202, then I'll see you guys in a few hours. So bye.